तो ये मेरा ही तो है, ये वाला पार्ट, ये वाला नहीं है मैम का, मैम का नहीं है। इस बार इसको जॉइन करने के साथ ही मेरा देख रहे हैं।
First of all, a very energetic good morning to everyone. My name is Pushpalata Thakur from MSc Mathematics 3rd semester.
And my name is Dipshikha Paul from MSc Mathematics 3rd semester. It's really pleasure to have you all for a cause that unites us. We are united through mathematics, and mathematics is a language that speaks to the logic within us all.
We are gathered to gain deeper insights on mathematics through global initiative of academic networks, in short GIAN program, initiated on November 30, 2015 by the Ministry of Human Resource Development in India, aimed at tapping the talent pool of scientists and entrepreneurs internationally to increase their engagement with institutes of higher education in India, to accelerate the pace of quality reform and elevate India's scientific and technological capacity to global excellence. This program provides participation of foreign faculty as a distinguished visiting faculty, professors of practice, etc. in delivering short or long courses in IITs, IIMs, central universities, and subsequently cover state universities.
To proceed the program ahead, on behalf of Department of Mathematics, School of Mathematical and Computational Sciences, we would like to invite our beloved Professor Amit Kumar Saxena sir, Director of IQAC, and expert Professor Besile Brende sir, Professor P. Viramani sir, Registrar Professor A.S. Ramadive sir, Course Coordinator Professor P.P. Murthy sir, and heads of mathematics and CSIT department to lighting the lamp, to worship Goddess Saraswati and pay tribute to Indian mathematician and number theorist Sir Srinivas Ramanujan.
इसमें पूरा चेंज करना पड़ेगा। आपका है ये वाला पार्ट ना, कुमार सक्सेना फ्रॉम, ये तो पूरा कैंसिल, ये दोनों कैंसिल। अच्छा, इसमें आपको बोलना है। हाँ, नेक्स्ट टाइम भी आएगी। उसके बाद फिर आपको बोलना है धनंजय गोपाल सर का रटन इधर का रहने देते हैं जैसा है, उसको दिखाना लिख लेते हैं पूरा अमित कुमार सक्सेना। ये डायरेक्टर ऑफ IQAC है। सरस्वती बंदन में कौन गा रहे हैं? ये वाला नहीं है फिर। I would like to invite फिर वही respected professor सक्सेना सर का स्पीच नहीं होगी क्या? किसका? सक्सेना सर का वो बुक होगा ना, होगा बुक में वो किया होगा ऐड करो तो उसी की जगह तो इनवाइट द के बाद क्या रिस्पेक्टेड में डालो। नहीं, वो तो चीफ गेस्ट है ना, तो अनरेबल ही रहने दो या फिर रिस्पेक्टेड में सर मना कर रहा था। प्रोफेसर अमित कुमार सक्सेना। टू क्या बोलूँ? अलग से एक्स्ट्रा मत करो, डायरेक्ट इन्वाइट करो। कुमार सक्सेना, ही इज़ डायरेक्टर ऑफ
अम्मा खाने की ऑफर
शायद क्या था, IQAC CSIT डिपार्टमेंट, पता नहीं। ये वाला पार्ट तो है नहीं, ये आप बोलोगे?
आप
कि
ही
मैं
के
बोल
मार
लूँगी?
आप ही के मार
ये वाला तो नहीं है ना मैम का?
काट दो, कंफ्यूजन हो जाएगा।
हाँ, क्योंकि इधर से भी है, वाला नहीं होगा, इसको ठीक कर दो।
अमित कुमार सक्सेना को सर को देना है मोमेंटो।
ठाकुर सर को नहीं बुलाना है, असिस्टेंट प्रोफेसर को देने के लिए। बाकी टीम्स को भी बुलाए हैं तो उनको भी ऐड करना चाहिए था ना, हेड्स ऑफ CSIT और मैथ्स डिपार्टमेंट ही बोले बस।
नहीं, थैंक यू बोला आपका।
ठीक है,
मैं फोन करूँ।
आ जाइए।
सर क्या साहब आइए, आपके काठमांडू यूनिवर्सिटी से भी आए लोग। हाँ काठमांडू की गूगल
वही है ब्लू वाले। अरे यार मेरे को पहले
वही हो रहा है।
बोल रही थी वही ब्लू वाली है, अमित कुमार सक्सेना।
Following the rituals of Atithi Devo Bhava, that is, guest is our God, we would like to invite Professor P.P. Murthy sir to honor our Honorable Professor Amit Kumar Saxena sir from CSRT Department, Director of IQAC.
Following this, we would request Dr. Dhananjay Gopal sir to honor Registrar of our University, respected Professor A.S. Ranbir sir.
Again, we kindly request Professor P.P. Murthy sir to honor our esteemed chief guest, Professor Basile Brinde sir.
In this series, we would like to invite Dr. J.P. Jaiswal sir to honor with bouquet to our another chief guest, Professor P. Viramani sir.
After this, I would request Dr. Uma Devi Patel ma'am to honor with bouquet to respected Professor Zoita Brinde ma'am. Now, we would like to invite our course coordinator, Professor P.P. Murthy sir, for welcome address.
Good morning, one and all. Due to some health issues, I think our Honorable Vice Chancellor sir not able to come, but I need to say a few words to honor him on this occasion. It is my privilege and honor to welcome you all to this prestigious event under the global initiative of academic networks, an ambitious program initiated by Ministry of Education, Government of India to foster academic excellence and international collaboration. We are especially privileged to have with us Professor Arok Kumar Chakrawal, the Honorable Vice Chancellor of Guru Ghazidas Vishwavidyalaya, Bilaspur. Professor Chakrawal is not only an exemplary academician but also a dynamic leader, an inspiring motivator and an excellent team builder. His vision and dedication reflect in his strong belief in Sabka Saath, Sabka Vikas, ensuring inclusive growth and collective success for all. Under his guidance, Guru Ghazidas Vishwavidyalaya has reached new heights of academic and institutional excellence. Today's program embodies his values of promoting global academic synergy and nurturing young minds to become leaders of tomorrow. On behalf of everyone present, I extend my heartfelt gratitude to Professor Chakrawal for gracing this occasion from where he is at home right now. We eagerly looking forward for his insights sometimes in our program. I would like to extend my welcome to our Honorable Senior Professor of our school, Director IQAC, Professor Amit Kumar Saxena, who is always brotherly to the mathematics department, and his excellence in programming, data mining is no words to say about his research contribution. He has good insight for the futuristic development of the university and department, and now he is the director of IQAC. I welcome you, sir. I have no words to speak in particular about Professor of Birende, Basil Birende, who is a distinguished mathematician and a globally recognized expert in nonlinear analysis, particularly in metric fixed point theory. And Professor, about the professor, I will speak a lot of things later on. A few things I need to share about the professor. The professor is a BS and MS degree in computer science. He is BTech in computer science, MS degree also in computer science, and later on PhD in mathematics. So whenever he used to write the research papers, you can find good algorithm. So we are sharing also that, so he is having the good idea of the algorithm because his background is a computer science. He has been recognized as the highly cited researcher in 2016 and 2017 by Thomas and Reiter, and has been consistently featured in the Stanford University World Top 2% Scientist list for the year 2020, 21, 22 and 23. Professor Birende has several various leaderships. Few things I have to cite here. Right now, he is the coordinator of the Ministry of Education's Committee for the Accreditation of Mathematics Higher Education Programs. Professor Birende is full member of Academy of Romanian Scientists and served as the Vice President of the Romanian Mathematical Society from 2012 to 21. He is the founding editor-in-chief of the Carpathian Journal of Mathematics, Q1 SCI, and is on the editorial board of other leading journals in nonlinear analysis. When his speech comes, I will talk more about him. Professor Veermani, who is a great mathematician, and for the next 5 days you will find that how he is so simple in approaching you people, or you can approach him via mathematics. It is an immense honor to welcome Professor P. Veermani, a distinguished mathematician and a leading expert in fixed point theory of IIT Madras. He retired from Department of Mathematics from IIT and has had an illustrious career marked by significant contributions to fixed point theory and applications, game theory, best approximation, and fuzzy metric spaces. So when today afternoon he will deliver a lecture on functional analysis, so we shall introduce him more. Now we are delighted to recognize the invaluable contributions of our energetic and dedicated registrar, Professor Randive, whose efforts have been instrumental in driving the growth and development of our university. He is a very good mathematician also. Professor Randive's dynamic leadership and unwavering commitment have ensured smooth administrative and functioning while fostering an environment of academic excellence and innovation. His proactive approach and vision have been pivotal in implementing key initiatives that have strengthened the university's infrastructure, academic programs, and community engagement. With his exceptional organizational skills and forwarding thinking mindset, Professor Randive continues to inspire all of us to work forward towards the shared vision of excellence. I would like to share few more things. Professor Gaita Birende, who is happened to the wife of professor, she is also the professor of chemistry of university, in Technical University. We welcome you, madam. I also welcome all our deans of various schools, heads of various departments, participants from many parts of the country, and two countries people are here. One is from Nepal. Right now actually 4 are supposed to attend, but now 3 students, research scholars from Nepal, they are attending, and 1 faculty member from Bahrain. So, sir, this program is a webcasted program. Webcasting is going on with 30 minutes to 20 seconds to 30 seconds delay. And this program is also available on Zoom. And this program will last from 25th of November to 29th of November. We are frequently interacting with the participants by our group in the WhatsApp. We have made almost 20-25 days back. All our faculty members, all school faculty members, our students, PG students, and staff of the university, VC office, registrar office, and all those friends who invited here, and they are present for this ceremonial welcome. So once again, welcome you all. Thank you very much for giving me the chance to welcome you all. Thank you, sir.
Thank you very much, sir, for introducing such inspiring personalities. Next to share his insights, we would request the senior most faculty member of Mathematics Department and presently Registrar of our University, respected Professor A.S. Randiva, sir.
Thank you. First of all, I will like to express my gratitude and thankfulness to the Vice Chancellor, Professor Alok Chakrawal, for building up the university within a span of 3 years. The university has changed itself dramatically. As he has a busy schedule, yesterday also he was very busy and not feeling well. Today also there are some interviews, he could not make it to come over here, and in his absence, to grace the occasion, Professor Amit Saxena is with us. Professor V. Merinde from Romania, Professor P. Veeramani, who has been very well known to various faculty members of our department, Dean of the school, Professor Murthy, Head Department of Mathematics, Professor Thakur, Mrs. Dr. Rita Berende, various deans from schools, Professor Anupama Saxena from Political Science, various heads from departments, and dear colleagues, students. It is a great opportunity to have a program like GIAN. It gives you a direct opportunity to be in touch, rather in personal touch, with the leading mathematicians of some particularly chosen branch. Because in fixed point theory, there are 6 to 7 faculty members working on this particular area. I also worked for some years, and now I have once again shifted over to some applicative aspects of fuzzy logic. This branch of mathematics has always attracted mathematicians from all corners of the world, and if I am not wrong, it was many times felt that we have come to a point of saturation in fixed point theory, but then someone gives a new idea, and as we always have this known to us, that as you move upwards in the flow of the knowledge and as your vision makes the things clear, various branches of different disciplines, not only mathematics but various other branches, come together, and we can find some application on such areas where it was not earlier possible for us. For this, a visionary person, a leading mathematician or someone is needed. Mathematics is little bit introvert in nature. The subject itself is introvert. So all the personalities and all the teachers or students are obviously becoming a little bit introvert, because the subject tends them to make them introvert. But they can understand, yes, what is the importance of mathematics. We need not emphasize that how the things are changing due to mathematics. And once again, after 1965, when Lotfi Zadeh has given his most striking innovative thinking in mathematics, fuzzy set theory and fuzzy logic, the entire universe of mathematics has reoriented. We have shifted our origin of thinking, the Aristotelian logic, which was the base of all mathematical thinking, and which, due to its nature of being stringent in measurement, only yes and no, and nothing in between was allowed. But when this striking change came into the area of mathematics, and it was acknowledged by every, not only by every mathematician, but it has been acknowledged in every walk of science, every walk of any other discipline. And recently now we find our applications in judging what will be the next election results. Many things such will be coming up very slowly, because the branch which I am talking about has just initiated in 1965. History of mankind is more than 5,000 years old. We have traces of mathematics and mathematics knowledge more than 5,000 years old. So in this long tenure, if we call 1965 onwards, so this group is only for say 50 years. It is very small period, but this change of origin of thinking will be an important point in the application of mathematics in the real world scenario. As we move forward, we will find the application of fixed point theory also in every walk of life. And as we move forward, we find that it has close interactions with certain other branches of mathematics. So this is a superb opportunity, not for the students of Department of Mathematics, but various research scholars and faculties coming from all over country to have an interaction with such type of two experts, and for a span of 5 days personal contact will be available to you. I hope you will explore and exploit each of these opportunities coming across you once in a time. So I wish this program a great success. Thanks for inviting me. Thank you very much.
Thank you very much, sir. Such a compelling speech it was. Your passion and expertise shine through. To be inspired is great, but to be an inspiration is an honor, and they are inspiration for us, and we are excited to listen their experiences of how hard they worked to make changes in various fields. Now, we would like to invite Professor P. Vinamani sir to share his wisdom. He was Professor of Mathematics Department at Indian Institute of Technology, Madras, Chennai, Tamil Nadu.
Good morning. Hello to everybody. I'm glad to be here. I'm really impressed by the great interest in this GIAN course. I am committed to bring some of the knowledge of my experience in research here. Now the research, the science is global, and this project, Global Network, it's a very good opportunity to come here. I congratulate Professor Murthy for having this idea, for providing a good project that has been approved. Well, many years ago, he invited me. I forgot about this involvement in this program, but anyway, I was able to come due to my very busy agenda. I had to change something in my agenda. I'm really happy to be here. And I do hope you will find some human side of the research activity from my presentations, more than the research and the results of the research themselves. Maybe I should take the opportunity my pre-opponent said about something about saturation. I'll speak about, I introduced a concept of saturation in fixed point theory, and I was inspired by the activity of my wife. In chemistry, saturation is very natural concept, and so I'll speak about this saturation in fixed point theory and unsaturated aspects. Well, let's hope we'll work together very fruitful. I know you are interested to know what I'm speaking here, and I want to say that I'm really honored to be in the same team with the reputed Professor Vera Mani, who is an extraordinary deep researcher in this field. I have a great admiration for him, and I'm honored to be in the same team. So all the best to you. Thank you, the local leading administration. Hope to be a nice and fruitful event. Thank you.
Thank you, sir. We are deeply grateful for your presence here throughout the workshop and for in-depth work in mathematics. Your insights have truly enlightening. Mathematics knows no races or geographic boundaries. For mathematics, the cultural world is one country. Now we would like to invite Professor P. Viramani sir to share his wisdom. He is Professor of Mathematics Department in Indian Institute of Technology, Madras, Chennai, Tamil Nadu.
At first, I would like to thank Professor Murthy, all the Vice Chancellor, Director, Registrar and other Professor Deans and all of you, Professor from Maths Department and other department and participants for this program. We do hope we have an excellent Professor Perende, who is an expert in this field, and we were very fortunate that he has accepted the invitation and he is going to be here for all the 5 days. We do hope you will all enjoy and interact with him. So we just don't want to state the results, learn the basic concept, understand and do some meaningful work. We are in front of the man who knew infinity. With his blessing, we will try to understand the concept of infinity, maybe under epsilon. When many times epsilon means, they say maybe when we talk, we will talk about that. In fixed point theory, applications are not limited only to mathematics. We are all familiar with the differential equation, integral equation, functional analysis, including very famous problem, invariance of space problem, mathematical economics, and many other field, engineering and other field. So, have you heard about beautiful mind? Some of you might have heard. Nas, when he was just 21 years old, he introduced a concept, later it is known as Nas equilibrium point. Later, that concept, that the existence of Nas equilibrium point, you need a fixed point theorem to prove the existence. It is just, I think, 2-page paper. Later, it got Nobel Prize. As you know, there is no Nobel Prize in mathematics. We have only field medal once in 4 years. But Professor John Nas, much later, during 90s, he received Nobel Prize for his extraordinary work in mathematical economics. So, we understand, appreciate not just mere generalization, why we introduce, what is the need and how to proceed. Hope we all are here, you interact with all of us, and we do hope you will, when you go back, you will have a different feeling and do good research work, and that we hope that you will get motivated and do excellent work. Again, I would like to thank all the members for giving this excellent opportunity to be here, and thank you all to be here. Thank you.
Thank you very much, sir. Your speech was truly inspiring, and we can't thank you enough for being a part of our workshop. Your words will resonate with us for a long time. Next, I would like to invite Professor Amit Kumar Saxena, sir, to share his wisdom.
Thank you. Good morning, everyone. My highest gratitude to our Honorable Vice Chancellor, Professor Alok Kumar Chakravarti. Due to some health issues, he could not make it, but his presence is always very exciting and very motivating to all of us. Now I welcome Professor Brinde Vasile from Romania, our Dean, Professor P.P. Murthy ji, and who is also the convener of this event, Professor Veera Mani ji, Professor A.S. Randevi ji, Registrar, Professor Thakur, the head of the Department of Mathematics, Professor Anupama, Professor Joita Madam, Professor Mehta, Professor Tiwari ji, Professor Bajarwal ji, our Dean Student Welfare, Professor Salan Kumar ji, Professor Srivastav ji, Professor Vijay Tiwari ji, our Controller of Exam, Dr. Sampunan Jha ji, Madam Seema Rai ji, Dean Professor H.S. Tiwari ji, our all faculty members, all deans, Professor Anant Tripathi ji sitting on the second, all deans, all faculty members of Department of Head of the Computer Science Department, Professor Ratnesh Srivastav ji, all faculty members of the schools of Mathematical and Computer Science, Mathematics and Computer Science, the PhD scholars of the school, the students and the staff engaged in this hall. This is really a very exciting moment for all of us. The Department of Mathematics, this is I think in the second in continuation, the GIAN proposal, and I congratulate Professor Murthy for being the convener of both the events, and this is our privilege that this very innovative event is going on in our university. In many other departments also this program has already been conducted. English, biotechnology, several other departments have also conducted this event. The mathematics is the bone of, because the school is mathematics and computer science. Mathematics is the backbone of computer science. We cannot live separately. So the theory of, as I can see, the recent trends in metrical fixed point theory and application will be a very challenging and very useful topic for all the attendees. The scholars who have come all the way from abroad, that is a great chance for all of our PhD scholars, for our faculty members to get the best of the knowledge, as you have the very rare chance such type of professors are coming. Last week I had a chance to visit Bangkok Thammasat University, and there is also a very huge group of fixed point theory. Professor Cho, I could meet him, and Professor Beautiful was also there. So I had a chance, because I was invited for my talk on machine learning. So I could see that they have a very big group, huge group of fixed point theory, and even the group is as good as like a subject. So I can understand the importance of the topic which is being conducted here, and our Honorable Vice Chancellor is always very encouraging and motivating to conduct all such activities. I wish that all the experts who have come from abroad should have, they are very healthy and very pleasant stay. Please have a visit around the campus. We will find that we are very cautious about the environment, about the fresh air, about so many health related things to our campus.
I invite all of you, please have a campus visit and request Professor Murthy also to take them around, because this is a golden moment for all of us that we can share exchange our knowledge during this 5-day, during this week-long program. So once again, I thank you all of you, and especially the external Professor Birinde and Professor Veeramani ji, Madam Dweta, for coming to here and sharing their excellence in our campus. Thank you very much.
Thank you so much, sir. Your remarks have been highlight of our event, and we are so grateful for your willingness to share your knowledge and experiences. Now, I would like to request Professor P.P. Murthy, sir, to present memento to Honorable Professor Amit Kumar Saxena, sir. Following this, I would request Dr. Poti and V.V. Prasad sir to present memento to Registrar Professor A.S. Vanvive sir. Now, we would like to invite Head of Mathematics Department, Professor A.K. Thakur sir, for vote of thanks.
Good morning all. I feel honored and privileged to get the opportunity to propose the vote of thanks on the GIAN program. I would like to thank all the honorable delegates and speakers, invited speakers, who have blessed with us and their presence. I, on behalf of the Head of Department of Maths, convey the deep regards and heartfelt thanks to Honorable Vice Chancellor Sir. Due to health problem, he is not available with us, but his blessing, constant help, motivation and guidance that relates a source of energy for all of us, which formalize the conduction of this GIAN program. Thank you once again, sir. I thanks to Professor Amit Kumar Saxena sir for his blessing and guidance and support. I am also thankful to respected Registrar sir, respected DSW sir, respected Finance Officer sir, respected COE. They have helped in obtaining the necessary administration approval for organizing this event. My thanks to Professor Birinde, Professor Veeramani for his gracious presence. I would like thanks to the course coordinator, Professor P.P. Murthy, for his constant effort for organizing this GIAN program. I am thankful to all the faculty members, research scholars, PG students, and non-teaching staffs who always stand with us and motivate us. Thank you all for making this inaugural event successful. Thank you all.
Thank you, sir. We would like to invite Dr. B.V. Chaturvedi sir for an announcement.
रिफ्रेशमेंट के लिए और लोग वहीं बैठेंगे सर लोगों को सर
आइए प्लीज
सर डबल वन
आइए
Okay.
this GIAN 5 days workshop under the title Recent Trends in Metrical Fixed Point Theory and Applications. As I am in touch with you all for the past almost a month through the WhatsApp group, and almost at the end I have introduced our two eminent speakers, experts from the premier institutions of the world, Professor Basil Birinde and Professor P. Veeramani. Both of them are very close. Both of them have depth in the subject, fixed point theory and applications. If you Google, then also you can find. Professor Birinde, as I just now introduced, some partial introduction was given at the time. He is MS and BS and MS in computer science. Later on, completed his PhD in mathematics. And you can visualize his work, and you will find that a computer scientist is working as a mathematician. We have some interaction also. Yesterday, we three are interacting, and every day we three are interacting. Let me say our goal, what to achieve at the end of this workshop. Both will discuss fixed point theory and applications right from the initial concepts of fixed point theory. Few of you may know very well, or few of you may know little bit of it. As a student of this university or some other university, they have fixed point theory as one of the unit in the functional analysis. This I introduced here through the Brewers meeting around 15 years back, sir, around 2009 or 10. Fixed point theory, this one, and advanced functions. So this time, because of the large number of faculty members in the department, so we have to curtail. That's why we have introduced one as a compulsory subject. So our motto is to introduce the fixed point theory. So basics I have sent you also. I have sent all the preliminaries, sir. You can, I think you have gone through also. It is in the given what the flavors are given at the time of inaugural. So all those things you need to know for the better understanding. While delivering the talk, your motive is also what the speaker wants to say, what is the philosophy of the speaker. It is always good to try to read the mind of the speaker. It is always good. And fly or swim along with his philosophy to how to construct a problem. That is only the motto for this, to invite such eminent people. And you know very well that in this fast world, staying in one place 5 continuous days is not so easy to anyone. And that too also, Bilaspur is almost 2 and 2.5 hours away from the airport. Even though professors did this in the interest of the students, research scholars and faculty members, okay, of this country, I say, because we have many participants from around the country. I am not specific to the state, but around the country. There are few people who are online also. We have given them the Zoom connection because of the attendance of such participants, like few participants still left in Nepal, Bahrain, Uttarakhand, and some of the other Punjab state. So every day end, before you go, you always have some sort of assignments. Those who are not willing to continue in a research as a fixed point theorist, but whatever the time you are given here, or paying the time, not just because of the student of this department or the student who has come over here to know what is the trends of the research. Deliberations, you can learn a lot. How the deliberations are given, what is the way to interact, how to interact the participants, what is the participatory contribution of any research. This is not a conference. We have already discussed yesterday along with Professor Veeramani and Professor Virende that, sir, this is not a conference. This is a workshop, and we start from the initial concept to up to that concept what the professors have done. Rather than saying professors, they are very good research students. You can learn them even at this age. They are very senior to me. Okay? So I should take this opportunity to thanks the director, Murthy of IIT Hyderabad, who has given fundings to us by 8,000 USD for this 5 days GIAN workshop. The national coordinator of GIAN, Dr. Agrawal, IIT Hyderabad. Then the accounts department of IIT Hyderabad. Our local coordinator, Professor M.C. Rao of Guru Ghasidas Vishwavidyalaya, the management of our university, in particular our Honorable Vice Chancellor, Professor Alok Kumar Chakrawal, who has given lot of opportunities to every member of this university, always motivating. So thanks to him also, along with his better half, to thanks. He is also supposed to come, but due to some preoccupation could not come. So I once again welcome you all and just say a few things about Professor Virende, and then Professor Virende will start his lecture. As I said, he has published more than 200 research papers, okay, and particularly on iterative approximation of fixed points. And as I said, he has the top 2% mathematicians of the world. So you should feel proud that such a mathematician, and give a great claps to welcome Professor Pasile Virende. Okay, so I do invite. He has supervised 21 PhD students so far, right, Professor? 21 PhD students so far. And as I said, he is the reviewer, editorial board members of so many notified journals of the world, means world-class journals. So when the Professor Veeramani comes, I will speak about him also, what exactly the contribution of the Professor Veeramani. So Professor Virende, please.
Put somewhere to be free of holding it. Okay. Well, let's go to work now. My intention is to give you some ideas about what I did. It's not working well. So I would like to share some of my experience as a researcher, and as I promised during the opening ceremony, I would take any opportunity to show the human side of the research activity. Maybe you are here mainly for the mathematical content of this course. Once again, I want to congratulate Professor Murthy for obtaining approval for this course. I'm glad to be here, and I do hope you'll have the opportunity to learn something from my experience. So first of all, I would like to show you from where I come. This is Europe, and Romania, it's this country. Maybe you should come in front of the room. Please, there are many seats available. Just come and fill them to see, because this the screen is not so big, not so large, and you should see better. So come here. There are still 5-6 places free, even here. So this is the map of my country. We should know that the capital city is Bucharest. The main cities and the main universities are these ones. Main is now Cluj-Napoca, where I studied. I graduated here. Bucharest, Timișoara, once again, and Iași are the main universities in Romania. Baia Mare is here, just in the north. It's a medium, let's say average city with a medium university. So, as you could read in the material, my university joined, actually merged a technical university in Cluj-Napoca, and now we are a campus of this university in Baia Mare. A few words about Baia Mare. Baia Mare used to be a very important mining center, gold and silver producer, the most important in Romania, but now all mines are closed. It's a general policy of European Union to close mines and to take gold and silver from other countries. So in order to eliminate pollution, any chemical industry is polluting, and Baia Mare used to be one of the most polluted cities in Romania due to the chemical industry. Now it is very clean. It is a green city because we don't have any chemical industry now. So I want to introduce myself. Professor Murthy introduced me, but I would like to do from my point of view. So, as he mentioned, I graduated computer science. At that time, computer science and mathematics were slightly different, in the sense that 75 of the curricula was common. So just the last 2 years, in the bachelor degree were different. So the basic was mathematics, and computer science was a kind of a specialization in the last 2 years. So this happened when I was a computer science. I studied computer science. So I worked after graduating. In Romania at that time, the government offered a position to each graduate. This is not more valid. Now we changed our rule, so it's not more a communist government. The communist government offered full access to education to all people, jobs and houses, all needed. But the principle was all are equal. So but people are not equal. This was the wrong principle of this period. But anyway, at that time, when we graduated university, we got a position depending on your rank nationally. So first one took the first as they want the position. So I took a position in computer science. I worked there as a programmer. Then in 1990 I joined the University of Banach as an assistant professor. I did my PhD and then I have been promoted to associate professor after 4 years, to full professor after other full years, and since then I am full professor at my university, which now is part of Technical University of Cluj-Napoca. My university and it is a small university. And one of my big achievements was to got founding of the doctoral school. This was not usual for a small university. So this was one of my main achievements to get approval, because this was approved by the committee of the Ministry of Education, and starting from 2005 I started this program, and as mentioned by Professor Murthy, 21 PhD students finished PhD under my supervision. Well, I want to tell you some of my academic activity, because for me, unfortunately, or maybe fortunately, research was not the only one activity. Mainly I was a teacher, so I still teach with great pleasure. The subject I teach differential equations, partial differential equations. I teach subject which is for computer science. It's graph theory algorithms, or graph theory, as you wish. So I also teach for master degree students a course that I like very much. You'll understand later why I teach a course which is called Mathematics for Gifted Students, Teaching Mathematics for Gifted Students. This is my favorite course for master degree students who will become teachers. So Romania, it's a very small country in comparison to India, very small, 73 times smaller, but we are producing a lot of mathematicians, or very good mathematicians. We are exporting each year many very gifted mathematicians after graduating high school or after graduating university, and we still keep some for our country, but we are good producers. And the secret is that for more than 130 years we have a tradition in identifying talents, gifted people, and try to attract them to mathematics. Now things change it a little, but we still do it. So this course I teach is for teachers of mathematics, secondary schools, high schools, how to motivate
to identify gifted students and to motivate them to follow a career in mathematics, because my belief is that if you are gifted, you will do a good mathematics career and you will be able to do research in mathematics. So I did a lot of work for administration. How many? We are in November, so in March I stepped down, so I did almost 30 years administration work. Lot of waste of time and energy for administration, chairman of mathematics and computer science department for 25 years, and also dean of the Faculty of Sciences. And I was also involved as a founding director of the Doctoral School of Mathematics in this period. In 2012, we merged Technical University in Cluj-Napoca, so the doctoral school became larger. I also worked in what we call in my country work for the benefit of the academic community. This means editor, reviewer, organizer of conferences like Professor Murthy is doing now. I was involved for a quarter of century in the National Committee of the maths competition in Romania. We cultivate the passion for mathematics from 11 years. So we organize a national-wide competition which is called Mathematics Olympiad, which selects the best peoples, and we try to attract them to do mathematics. Fortunately, there are many. Unfortunately, from them, when graduating high school, not more than 10% go to mathematics, because the world changed, so now they prefer other professions like medicine, engineering, and some others professions, some of them far away of mathematics. But anyway, I'm confident after a strong mathematics education, they will become very good doctors, very good engineers, and so on. So we are happy with this. So I was in this national committee for many years. I was also involved in the leading of the Romanian Mathematical Society, which is an old mathematical society. I was for many years, 2 terms, member in the Mathematics Committee of the Ministry of Education. I was the chair of this committee for a term, and now I keep the position of the coordinator of the Committee for Accreditation of University Programs in Mathematics, Bachelor, Master, and PhD, because we have accreditation of all these programs each 5 years, so it's a periodic function. And last, I did research. Unfortunately, I said I did not invest more than 10-15% of my time to research, but I did with great passion. In the last years, most of my activity was focused on editorial. With my grandchildren. So what it remains for mathematics, for research, is just a little, but I'm doing deeply and with great passion. And this is what I want to suggest you. In order to be successful, I believe, this is my belief, in order to be successful in mathematics, we should keep balance in our life. Balance between research activity, between personal activity. When my PhD students, girls, married, girls, they are coming, Professor, I'm very sorry, but I got pregnant. I say,
I'm very sorry I have to interrupt the program because I'll give birth. I said, no, this is more important than any paper or any research. Do this and you'll continue after a break. And I insist on this, especially for girls. Girls, in my opinion, one girls matter as three boys. So this is my appreciation. So my wife counts as three men. They are professors, they are mothers, they are also taking care of the house, and we men, we are not very useful, just for some few things. So research I did with great passion, and as it was possible, I produced some research which I'm proud of. So I have some research. I would like to show you some of them, as I promised. But first of all, I want to show my academic children. So in this year, 1991, after 1 year I joined the university, I founded this journal. Now it is a Q1 journal. I'm proud of it, Carpathian Journal of Mathematics. It's indexed by Web of Science, SESCI. And I spent a lot of time with editorial work, so it's not easy. I also funded this journal which wanted to cover the starting research activity of young people. You can deduce it's creative, just to encourage young people to do research, not so important to be published in a highly ranked journal, but to publish the results of the activity. So this is the second consuming time activity of mine as an editor. If you want to know more about my activity, of course I forgot to tell you I organized many international conferences, summer schools, and so on. Here it's from such a conference, the picture on my web page. You can find some other facts. I did not update this web page for a long time because I'm really busy. I want to close this introduction by paying a tribute to my professor. He was my PhD supervisor. I am very grateful to him, and I do recommend you to consider gratefulness for your teachers. They are, how to say, like fathers for us, and I'm grateful to Professor Rus. He's 88, but he's still active. You can see he's born in this year. He founded the first research seminar in fixed and point theory this year, 1969. So this university, Babeș-Bolyai University, now, in my opinion, they have the best research group in fixed and point theory, 55 years old research group. Starting from this year when we celebrated 50 years of activity, the name was changed to nonlinear operators, differential equations, and applications to indicate that fixed and point theory has application in this area. And actually, fixed and point theory, I'll tell you if I have time enough, was born just from differential equation. So differential equation suggested to consider fixed and points tools. He is the founder of the Fixed and Point Theory Journal, a very well-ranked journal. Okay, it is better. I can skip it. Is it connected? Can you hear me? Okay. So he founded this journal in 1981 under this name, Seminar of Fixed and Point Theory. It was actually a journal
kind of proceedings of the seminar, of the research seminar. And he published this number of papers, very impressive. He's still active, you can see. He published in the last 10 years, he's 88. So starting from 78 to 88, he published these numbers of papers, very active, and he's still asking me, Vasile, let's do this. And I say, Professor, I'm very busy, I can, no, we should do this article, this paper together. And now we are working on this, on such a paper. And he is very well cited. He produced 27 PhD students, and I am proud to be his first PhD student who graduated in this year. I produced, this is from a mathematics genealogy project, if you know, where we register. And my professor did his PhD thesis in differential equations. And working on differential equation for his thesis, he identified the role of fixed point theory. And so he became the founder of fixed point theory in my country and one of the leading experts and founders in the world. Now it's time to go to our work. So, my plan is to tell you some things about the fundamentals of fixed point theory. You are familiar, maybe all of you are familiar with the Banach fixed point theorem, which Banach stated in 1922. This is the original statement. He stated this famous fixed point theorem in 1922 in what we call now a Banach space, which is a complete norm linear space or vector space. Something wrong? So what happened actually? Picard in a series of papers starting in 1890 devoted to differential equations, he used what we call now Picard iteration, that is, for a map T we define this sequence, which is a sequence of successive approximations or Picard iteration. And what he did, in fact, he did the following. He transformed the differential equation and identified, in his case, the right hand side name part of the equation was a function of two variables, but I write it as one variable. And his method was based on this fact. Applying the fundamental calculus theorem, he used this, and he realized that if the derivative is less than, let's say, alpha less than 1, then he can prove the convergence of the sequence associated to a differential equation. So this was done by Picard. And what was the explanation? That Banach converted this idea, this method, into a very general. The secret is that Fréchet, another French mathematician, introduced what we call now a metric space. So Banach took this new notion and had the idea, and he realized that this
technique of Picard can be stated in a very general setting, in what we call now a Banach space. And this is the extraordinary idea. Banach was a very, how to say, picturesque person. He did not study mathematics at all. When he graduated high school, he and one colleague of his, one classmate said, we know all mathematics. We don't need to study mathematics at the university. And one of them went to philology to study languages, and Banach went to engineering. He's an engineer, and his story is unbelievable. So he served in during the First World War, and he was sitting in park and discussing with a colleague, with a classmate, about Lebesgue integral. And one person was walking around their bench, and he heard about, you said Lebesgue integral? Are you mathematicians? And so we discussed, and this was Schauder, which is famous for his theorem. And Schauder discovered Banach and involved him, and Banach did his PhD in a non-conventional way, because he was not a mathematician, and his thesis is this one. So his main result is in brilliant mind, and he used to study, to work, not at his office or at home. He used to work and do mathematics in the bar, in the coffee shops. This was the way he was doing mathematics. Extraordinary. Anyway, let's continue. Then Kachopoli realized that this Banach principle can be stated and proved in a complete metric space. What I know now, we know and use it in this way. But it's important to say that the original version of Banach is used in application, mainly in engineering. More than 90% of applications are in Banach spaces, not only in this. So here it's the original statement of Banach theorem. You can see the contraction condition. This is the coefficient. It is written in French. And he just proved what we call the existence and uniqueness of the fixed point, nothing about the approximation of fixed point. After Banach established his theorem, people tried to apply its fixed point theorem to the differential equations studied by Picard. And it was a disappointment, because they realized they cannot prove the Picard's theorems using only this theorem, because it was difficult to apply. We know an ordinary differential equation is transformed into a Volterra integral equation, and it was not possible to work properly with this Volterra integral equation. So people said, this theorem is not useful. But another Polish mathematician, I forgot to this Bielecki, if I'm not wrong, in 1959,
he has shown that if we are in a metric space XD, we can construct a new metric, let's say rho. D is equivalent to rho, and under this new setting, the Volterra integral operator, it's a contraction in the usual sense of Banach. So this was the moment people said, oh, Banach theorem is really very important and useful. And you realize that since 1920 to 1962, because this was the moment some other theorem, there was no interest on this fixed point theorem. People said it's not useful, not interest. But after that moment of Bieletsky, and this distance is called Bieletsky norm or Bieletsky distance, he relaunched the interest for fixed point theory. And this can be considered the real moment the fixed point theory started to exist. And there is an Indian mathematician, Kanan, who did the first important contribution regarding this. He considered what we call now Kanan contraction condition. Instead of considering this contraction condition, he took these two distances. Took these two distances, and he has shown that the conclusion of Banach fixed point theorem holds even if we have this condition. And what is important, while T in which satisfies the Banach contraction condition is always continuous, a map T which satisfies the Kanan contractive condition is no more continuous. And this is a very important moment in the history of fixed point theory. There are many other important conditions I mentioned here. This nice combination of Banach and Kanan done the same year, you can see. Chirich 1971, Reich 1971, and Professor Ruz 1971, but the paper was published in 1972. So all these three mathematicians unified Banach and Kanan's fixed point theorems to get the same conclusion. This map, a map which satisfies this condition in a complete metric space, has a unique fixed point, and we can approximate this fixed point by Picard iteration. And of course, when B is 0, we get the Banach contraction condition. When A is 0, we get the Kanan contraction condition. As I know, Kanan, maybe I'm wrong, Kanan moved to the United States, and he was working in computer science, I guess, rather than in mathematics. At least I know. Okay, at this moment I want to draw your attention to the following fact. Now, one person here present at the opening ceremony that in some sense fixed point theory is saturated. He is quite right in some respect. What does it mean? People are introducing a lot of so-called generalizations. So what does it mean, generalization? We start from a theorem, or from many theorems, in a certain setting or under some assumptions, and we obtain theorem 1a. And we pretend this is a generalization. So this is not a generalization. If we do not show concretely that we can give an example, at least an example, that this theorem works and this theorem do not work. So these three mathematicians, Roos, Chirich, and Reich, all did this. So Roos presented this example. He has shown that this mapping T satisfies CRR, Chirich, Reich, Roos condition, but does not satisfy neither Banach, because T is not continuous, nor Canaan contractive condition, because we have this contradiction taking x1 over 2 and y1. So this is the way we should improve results in fixed point theory. A generalization which is not shown to be an effective generalization is not a generalization. And there are, unfortunately, there are many such kind of results. I speak here as an editor. So as an editor, as a reviewer, I always ask authors to provide proof that their new results are really new, are effective improvements of the existing results. So the same did Reich. His example is also nice. The same has shown that I did not include the Chirich examples. Now, another Indian mathematician, India contributed to this field much at the beginning, and now there are many. I'm surprised how many people are interested in fixed point theory. Chatterjee published his paper, I'll show here, just to, sorry. He published in a journal, Bulgarian Academy of Sciences in this year, and he used a kind of dual condition in comparison to Canaan, and he did the same. He shown we have the same condition. I did not read here the author, is Zamfirescu, sorry. Zamfirescu is a Romanian mathematician. He was very young when he provided this nice theorem. I insist on this because it is the starting point of some of my contribution in fixed point theory. So you have seen, Chatterjee is with dx ty dy tx. Canaan is with dx tx dy ty, and Banach is with only dx y. So, sorry. Zamfirescu proposed this very nice theorem, and the statement is very easy. We have a complete metric space, we have a map T, and if for each pair of x and y, if at least one of the three conditions is satisfied, then T is a Picard operator. What does it mean, Picard? This notion has been introduced by my professor Roos, so means that this map has only one fixed point, and the sequence of successive approximation converges as n tends to infinity. This means Picard operator. Banach, it's a Picard operator, Canaan is a Picard operator, Chatterjee is a Picard operator, Zamfirescu mapping is also a Picard operator, in the sense we have unique fixed point and the sequence of successive approximation converges to this fixed point. So here it's a diagram. Zamfirescu in his paper, at the time, it was about 1999, I was teaching a course exactly fixed point theory. At that time, in Romania, the bachelor degree was 5 years. Now it's 3 years. So they shortened, and in the last year of study, so in the 5th year, we had some special courses, optional courses. So I taught this course, I enjoyed very much, and I came across with the theoretical fixed point theorem, and I was unable at that time. A break. You should understand how easy it is now to do research. You have access to a lot of information on the internet. At that time, we already had some databases, but in 1980, in order to get a copy of a paper, we used to write a postal card to the author and please send me a reprint of your paper. This, for example, I sent to Australia. It took 1 month to get the answer. Now you can access the paper, or at least some review on that paper immediately on the internet. So at that time I was not able to get a copy of this paper because in Romania this journal was not in the libraries. Any mathematical library did not have this journal in their collection. So I tried to prove this theorem, and first of all the idea was that Banach condition, Cannon condition are independent, and also Chatterjee contractive condition is not put here, are independent. Here is just the Chirich-Reich rules which unifies the conditions Cannon and Banach. And Chatterjee will come something here. I knew I draw it, but it is not here. So during this, teaching this course, no, not yet, I tried to prove myself this theorem. And I did several trials. I do this in front of my students, and I'm not ashamed if I do not succeed to prove something. Some of them, Prof, could you prove this? Let's try. And for this theorem, I really told my students, I don't know how to prove this theorem. Let's try together. And during the tutorial, we did some steps, and we were not successful to prove Zamfirescu fixed point theorem, because it was unusual. So for each pair, so we are on Banach condition, for other pair x, y, we are on Cannon condition, for another pair x, y, we are to Chatterjee. So any kind of combination, how to master this, how to deal with them, and in the end, I succeeded, and this was the moment I discovered a new class of really impressive mappings. But first, I want to close this section by telling that there are many contractive conditions. This American mathematician in 1977 did classifications of this condition which arise from Banach contraction condition, and there are mainly 25 conditions, main. Banach is the first, Cannon is fourth, and so on. And all these, almost all, these conditions are stating their conclusion is that if we have a mapping in a complete metric space and it satisfies such a condition, then T is a Picard operator. This means we have unique fixed point and the Picard iteration converges to this fixed point. But this theorem shows that from a theoretical point of view, these many theorems are actually equivalent to Banach fixed point principle. Why? Because look, there are only two parts, two items in this theorem in the book of Professor Roos, and Petrushel Adrian is his second PhD student, and Petrushel Gabriela is the wife of Adrian Petrushel. They wrote this very important monograph in fixed point theory. If some of you want a copy of this book, I can provide you the file, the PDF of this. Is very useful for those who are interested.
I have a hard copy of this. I used to provide.
Okay, I can provide the soft copy of this and to spread to all of you.
Yeah, please send it.
Because when you work in this area, this should be the Bible. So you should read and see what was done, okay, until 2008, because this was the moment the book has been finished. And in this theorem, what is the idea? If we have a non-empty set X, we have a map T, self-map, then these two statements are equivalent. If there is a metric D on X such that this map T is a Picard operator, in this sense, I have written here, this is equivalent to the fact that we can find the constant alpha, we can find metric, complete metric, I forgot to put here D, on X, such that this map is in fact a Banach contraction. Well, from a theoretical point of view, what does it mean? That tens, hundreds of fixed point theorems which have this conclusion, T is a Picard operator, are equivalent to the Banach contraction principle. But this is in theory. In practice, it's not easy to find this metric, to construct this metric. So these theorems are important. So canon we can apply to some kind of problems. Chatterjee to some kind of problems. Recently, I attended a workshop in Belgrade, in Serbia, and there is a lady, Maria Cvetkovic. She is working in fixed point theory, and she's interested to construct such equivalent, such metrics. So we have a Picard operator, and to try, and she did for Canan. She did for Canan, she obtained a metric, and under this metric, the Canan theorem is equivalent to the Banach fixed point theorem. But these theorems are nice, and one of the nicest theorem here is the Chirich fixed point theorem I mentioned here. Chirich is this mathematician. They pronounce Chirich. I went in Belgrade to give homage to Chirich. I did not meet him in person, but we have some correspondence, and he was a very great mathematician. He is, by the way, founder of fixed point theory in Yugoslavia, former Yugoslavia, in Serbia. And his condition is this one. Is the most general. So it includes all these distances. dy, ty, dx, ty, and dy dx. Very nice condition, and the most general in this class of conditions. Rhodes, by the way, I speak when I reach the applications of these theorems. Rhodes was an American mathematician. He visited 2 times my university. He was a very interesting person, very nice person. He was enrolled in the army, U.S. Army, in the Second World War. Very impressive. And he did this classification just to show which condition is more important than the other one. I do recommend you this paper by Professor Roos, the theory of a metrical fixed point theorem, because he did in 2008, how to say, a look on all these fixed point theorems and pointed out what is important from the theoretical point of view and from the application point of view, how relevant are these fixed point theorems. And now, as I promised, I'll show you how I obtain a new class different from all these mappings, and I insist on this methodology. I did not include in my presentation, I'm sorry, I had no this idea. I teach a course to master degree students, methodology of scientific research. I like very much this course because I try to teach master degree students how to follow research work. The first question I put them is the motivation. Why are you interested to do research? So this is important from the beginning. Why are you doing research? So I have some answer to this question for them, and I mention here one. So most of us, you and me, we did research because we were interested in academia, and in academia to be promoted, you need to get PhD first, and then to publish more. You know, the Americans have this expression, publish or perish. So publish or die. If you do not publish, you'll die as an academic. So this is one motivation. But believe me, I know people who are not in academia, they are not professional in mathematics, but they are doing research by their passion. They are extremely passionate to do mathematics. I even know doctors who were very good in mathematics in high school, and they are still, we have in Romania a very famous journal, Gazeta Mathematica. This means Mathematical Gazette, founded 1895, continuously published, very prestigious journal, but it is now for high school students mainly and for teachers. And this journal contains a lot of mathematical notes, problems, and I know such kind of person, doctors or engineers, they have this journal for, as a hobby, to work on some problems. But mainly we are doing research because we have this professional motivation. We seek for a position, we seek for a career, and this should be, in my opinion, the most important reason to do research. And when I teach this course, I
present a lot of things, including my experience as a young researcher and what is needed to do, and maybe I'll have time later to show how we should proceed when doing research. Nowadays, it's important. This is the most important, in my opinion. Documentation. What is documentation? We should know what's happening, because I've seen several papers, they rediscover facts that were discovered 50 years ago, 70 years ago, and they are not aware. Well, sometimes it happens because at least in Romania, some important results were published in some journals written in Romanian. They had no international circulation, they were just locals, and people were not aware of some results. But first of all, we need documentation. And I use a book I like very much. I wrote this for this course. Exploring, investigating. This is the title in English. I published first an edition in Romanian. And discovering in mathematics. You can Google to see it. It was published by this prestigious publisher in Switzerland, Birkhäuser. 2004, this is the second edition. First edition was published in Romania. And here I show for some elementary cases, some elementary problems, how we do perform research work. So we explore, we must be fully, and we fully understand what is in a paper, a source paper, the original source. Then we investigate what can be done, what can be improved, if any, and then if we are doing this very deeply and constantly, we'll get the discovery. And this is what I want to show you that happened with me when I tried to prove Zamfirescu fixed point theorem. So, if you remember Cannon condition, I realized then I can write it in this form. After applying two times the triangular inequality. Triangular inequality, and we get this condition. This condition is obtained from Chatterjee, because there the coefficient was C, exactly similar. And here we have, in Banach condition, we have A less than 1. Here, this coefficient is less than 1. This coefficient of D of xy is less than 1. And I said, okay, but we can unify these two conditions and the Banach contraction condition into this, where delta is maximum of A, B over 1 minus B, C over 1 minus C, and so delta is for sure less than 1, and L is a non-negative constant. And I published a paper, this paper from 2004, this happened in about 2000-2003, this paper where I used for the first time this condition. And you can see here the proof, exactly the details of the proof, and this here is delta, so here is the condition. At the moment, I was interested for other aspects. L, this is L. After a while, I realized that I can use that condition
as a definition, I can use this condition. So this was the moment I introduced almost contraction. At the beginning I called them weak contraction. In the paper I published in 2003, and 2 in 2003, 1 in 2004. What is an almost contraction? We have a metric space XD. T is an almost contraction. I insist, I called it weak contraction, but I realized there are other concepts of weak contractions in literature, and then it came to me the idea to use almost, and almost there were not almost. So now it's recognized by most of the mathematicians as almost contractions. If there exists a constant delta in 0, 1, a non-negative constant L, such that we have this condition. Of course, it is easy to see that for L0 and delta equal to A, we get Banach. For for delta B over 1 minus B, we get GIAN, then we get right rules, we get Chatterjee, and many other conditions. Normally, I expected that this condition should ensure existence of a unique fixed point but it was not the case. So soon after that I realized that in comparison to this condition I have shown you, Banach, the coefficient of the right hand side is less than 1, the sum of the coefficients in right hand side is less than 1, all are less than 1, look, all important conditions. But for our condition, as you have seen, L is not required to be plus delta less than 1. So it can be, we'll see by some examples, even 6 or 7 or more. So this is the main result I want to mention it because of the difference of the all other theorems in this class of fixed point theorem. So we can prove in a complete metric space we have enormous contractions with coefficient delta and L, then the fixed point set is non-empty, no more unique fixed point, just existence, but the second part is valid, so for any x0 this sequence converges to some fixed point because there could be many, and we have this error estimate. So this error estimate has a story. I don't know if you are familiar with this term, is Latin a priori error estimate and a posteriori error estimate. This means that if I take here y equal 1 will give the a priori error estimate we have usually in the Banach fixed point theorem, less than delta over 1 minus delta b x0 x1. This is the a priori estimate, but we also have the a posteriori estimate. So here there are two examples. This map, which is very simple, has two fixed points and is an almost contraction with L equal 3. This map, again very simple, it's also an almost contraction with L6. It has two fixed points. And what is important, as I mentioned, all conditions, contraction conditions before are included in this condition. But however, this condition does not ensure uniqueness. So in order to have uniqueness, this is the graph of this of the second map. These are the fixed points. This one is 0 and fixed point 1 of the last example. So here are some important properties, and maybe we should take a break soon. In Romanian we have a very interesting saying. It's a poetry, but I shall translate in English. In Romanian it's pauzele lungi și dese cheia marilor succese. This means long and often taken breaks is the key for great success. So this, we should take some break soon. But of course it's a joke. So let's finish with these important properties, and I suggest taking a break to have a moment for discussion. So the most important properties, these kind of mappings are weakly Picard operators, in the sense that the set of fixed points is not empty, and this limit of xn is always a fixed point. So any almost contraction, this is definition of a weakly Picard operator, given the set by my professor Juan Ruz. So the same definition of Picard operator means one fixed point, weakly Picard operators means more than one fixed point. It is an almost contraction, or it's a graphic contraction. Graphic contraction is this one. So we have this condition which has been used by Banach himself in the proof. There is a graphic contraction principle that any graphic contraction has with closed graph is a weakly Picard operator. But these almost contraction operators are not with closed graphs, so they are examples of graphic contractions which are not with closed graph. Once again, this is a graphic contraction or graph contraction. What does it mean? We have Tx, T2x, x and Tx, and delta is the same like in the previous consideration, is less than 1. And one more property. If T is an almost contraction, then we have a partition of the set X, and the restriction of our almost contraction to each of these set is a Banach contraction. So we have this very important property. In fact, an almost contraction, it's how to say, union of Banach contraction, of many Banach contraction. And this example will show you. In the previous example, the two sets, we have two sets, 1, 0, 1 over 2, 1 over 2, 1, and here it is easy to show that the identity map T is a almost contraction, and if we denote each element lambda in 0, 1 by x lambda, then we have this partition, and T restricted to x lambda, which is a constant mapping, is a Banach contraction. So just to close with the uniqueness, in order to get uniqueness for an almost contraction, we have to impose an additional condition. And the condition is very similar to the original almost contraction condition. It is in this way, so we have exactly the same, theta is less than 1, L1 is non-negative, but here we have not y tx, but x tx. And then this map, it's a Picard operator. This means we have a unique fixed point, and all the other conclusions follow, including the fact that in that case we also have the rate of convergence. I speak at the end of this course about rate of convergence. What does it mean? This means that Picard iteration or sequence of successive approximation has linear convergence. Some of you or most of you should be familiar with Newton method, which is very important in application. Newton method is of order 2. It's has a quadratic rate of convergence, and it converges faster. So you, in general, fixed point iterative schemes are linear. Okay, here I suggest, if you can have a copy of this book, I've written in 2016 a review on almost contraction, so they are already 6 years on, but it's still useful. And here I want to say you, maybe you cannot read, this is the paper where I published this almost contraction. It has this number of citations in Google, 578. Most of the citations are in my book, Iterative Approximation, where this theorem is included. And also, this is the multi-valued variant. This is also related to rate of convergence, and also this paper with 200, almost 300 citations. So this had a very good impact, and there is still interest in this area, and I do suggest you to have a look at what always we can find something to do in any field of mathematics. My philosophy, because Professor Marty said about something about philosophy of doing mathematics. My philosophy of mathematics is that mathematics is a very large and generous field. It's place for all of us. It's a room we can do research, anyone, and in different manners. Just to try to find the arguments behind a theorem, behind the notion, just to fulfill what is this. In my opinion, documentation should be at least 75% of the work. We should try to understand, and when we do this, for sure we can get new facts. We can improve, we can advance in our field. Once again, we should prove that our advance is effective. So this is the next step. So first, to know no one did the same. By the way, when I realized this is a new, it was more than 20 years ago. When I realized this is new, I said, no, I cannot believe it's new, because lots of people work in this area. So I checked. It took me some months, maybe 1 year, to check all literature and to be sure it is a true result. By the way, I went to my professor, Ruth, when I finished the first paper, the proof, and when he saw this condition, he said, oh, this is impossible. I said, look, this condition is implying existence, is implying convergence of the Picard. He said, it is not possible. This is impossible. He had a look on the proof and said, this is really, really, really good and new, and that's the story. So I take the freedom to allow you for a well-deserved break. Okay? Well, You can, during the break, I don't know what are doing the organizer, we can discuss, you can come and ask for questions, or we just enjoy having this break. We'll continue after this break, let's say 10 minutes. Who is the responsible here? Prasad, you are you? Or, okay, yeah. We'll continue after a break, okay? So the president himself signed the PhD title. But he's a special case. He's, in my opinion, is it's a beautiful mind of his fixed point theory. Beautiful mind.
Actually, like the Ramanujan on number theory, you know very well that, okay? In a similar manner, if you more specifically talk about in functional analysis, so this man genuinely a Ramanujan, you can say. And there are some more interesting results you can find. And there are the people who are not from the same field, but they have done wonders in mathematics. There are some people, they never asked or begged for doctoral degrees, but they have done more than the doctoral degrees. That's true. And even there are so many people, even in our country where they are in schools, even not in colleges. Some people are only in colleges, not in universities or not in research institutes, but their research work is really remarkable. As Professor, who was talking about the Professor Rhodes. So since this is a gathering and we know, so sometimes we have to speak about something that you can find more interesting. He is the first person who invited me as a PhD scholar in 1989. Indiana City, Bloomington. So due to some family obligations and some other things, and my father was died later, so that's why I could not go there for pursuing my PhD from Indiana City, Bloomington, under supervision of Professor Billy Rhodes. 89, and we met in 2000. That is in Sicily, Italy. That is a WCNA 2000, organized by Professor V. Lakshmikantam, you know very well. He organized. There we met, we were stayed for 10 days. And really, as he said, a military man. Tall, more than 6.5 feet, tall man, and you can say lot of aggression, lot of interest in fixed point theory, and whatever he writes, normally he will not go to agree if anyone comment on his results. That is true. You observe or not, I don't know. Later his wife actually suffered badly, and he's supposed to come in the last GIAN program. I requested him also. Him and Mufti Zadeh also. Mufti Zadeh assured me that he will visit our university, and he told me that he is from the Berkeley. So he told me that funding is not a problem for me. I have very good funds. I will visit. But unfortunately, he passed away. Later, after some time, he passed away. His last 1 week or 10 days before letter is still with me, his email, Mufti Zadeh's. And Billy Rhodes also. Billy Rhodes' wife died, and later on he also passed away. Like he pronounced, we normally pronounce Sirik, but you see he said Chirich. The original pronunciation. Yeah, Chirich. That's why when he came day before yesterday, so I asked him how I pronounce his name.
But you don't know yet to pronounce it.
So within 5 days it will be done. Because like Dorel Mihach.
It's okay. Yeah, it's correct. But my name you should learn.
So last time Dorel Mihach visited, and I was also, because you can see in the videos that Dorel's name also, Mihach's name is not, spelling is different. So in Professors state also the same issue. Ask him how he will write Ajgaya. That is actually Aragaya. And how they write, right sir? So it is not so easy. Even in our country also you can find many, from Manipur side also very difficult to spell out their names. So I think very good lecture by Professor, and you will find everything slowly, but at the end of the last 5th day, you will find that you are something. But you have to focus. As I said, not necessarily you are going to pursue your degree in fixed point theory. See, especially, let me speak in Hindi, these people, because some of people are Hindi and they may be more touchy. आप इस बात की कोशिश बिल्कुल ना करो कि आपको किस सब्जेक्ट को बताया जा रहा है. आप इस बात की कोशिश जरूर करो कि आपको नॉलेज मिल रहा है कि नहीं मिल रहा है. The same three idiots dialogue. Gain the knowledge from anywhere, any quarter, any class, any subject, any branch of studies, and it is going to help you only. See the professor. Now I am also working on the data science. Almost I reduced my work in fixed point theory. I am now more focused on the data science for the past 3 years. And I have very good research project students, project students also. Every project student has to opt data science if he is choosing me. This is what I started. And professor is really from the computer science having very good algorithms, and these algorithms reflected in his research. Nobody knows that except that Picard's and later on the Newton-Raphson's method using the C programming language. Nobody is doing any algorithm. Now these days you can say very good number of algorithms in for obtaining the fixed points. Yes. You want to ask anything? Okay.
No, I guess the break was quite fine. Can we continue now? The second part. Okay. We want to break longer. Okay. A question? Yes, please.
One question. You have a question?
Yeah.
Please.
Thank you, sir. A relation between cannon type contraction to weak contractions, actually. How this is the weak contractions?
Weak was the first name of this almost contraction.
That means what is the difference between actually
cannon
contraction and contraction?
Contraction.
Weak.
Okay.
No, his question is something we can put in this way, that how you say that Conan contraction is weaker than the Banach contraction. Is this the question?
Yes, sir.
Right. Okay, he will explain very nicely.
So you mean how to show that Banach contractions and Conan contractions are different kind of conditions. The way we do it is to find simpler examples, and I have an example here. So just simple example. I can show you. Maybe I have not here. So the way we are doing, this is Conan, this is Banach, and this is Chatterjee. And these weak contractions are here, or almost contractions. And if you are interested, I can show a map here, which is Conan is not Banach. A map here, which is both Conan and Banach. Here a map T3, which is only Banach, not Conan, not Chatterjee. One map here, and so on. This is common here. It should be T3, 4, 5, 6, and 7. So if you are interested, I will indicate a book, and I can provide the PDF of this book. Just a moment. I guess I have somewhere. Maybe it is it's cited on some slide. Do I have internet here?
Yeah, you have.
You have.
You have? Can I? Okay, let's try. So what we have here, we have Chrome.
5 minutes break, because before the lunch, before lunch you have to sit. 5 minutes break you want? Huh? Professor, we give a break of 5 minutes and... Okay. Break for 5 minutes.
room if they have something like that. There is a router. I expected that from this router we can connect.
Yes, I am also found one router.
It's a router in the room, but it doesn't. Then indicated
dear participants, and when you are listening of the lecture, if you have any doubts, write down on the paper. After completion of the talk, then you can ask easily. So time saving also. Thank you very much.
All right, should we continue? So, because was a question about examples to delineate these classes of mappings, this is a very nice monograph, and you'll find all kind of examples to show which is different. So, it's a book, Iterative Methods for Fixed Point Approximation. This is the name of the publisher. Cluj-Napoca is in Romania, 2009. And if you need a soft copy, I can provide it. Maybe I thought to give you my email address, but maybe better I'll send to Professor Murthy, both the book by Ruth, this monograph, big monograph, and this one, and you can read. So this is full of examples, you will be satisfied with them. So let's go back to all right, so I just want to indicate how a new idea can be put in value, can be developed. I did myself just a few. I left to other young people, and there are at least some hundred of papers that use this almost contraction as a starting point, and there are many papers. I did not have seen all, I did not see all of them. All the time I said, oh, I should have a look on them, but I don't find time. So the first important development was to go from single-valued mappings to multi-valued. So we introduced, together with my co-author, Madalina, this important paper on a general class of multi-valued weakly Picaro mappings, which was published in Journal of Mathematical Analysis and Applications. And after that, this was the condition. And if you are not familiar with the Hausdorff-Pompeiu metric, this is the distance between sets. This definition has been done in 2 steps. Pompeiu was a Romanian mathematician. He introduced this distance in complex plane. He was doing his in the complex plane, so in R2, let's say, to introduce the notion of convergence of sets, of curves, actually. The sets in the complex plane were curves. He was doing geometry. And he introduced the notion of convergence of these curves, and he introduced this in his PhD thesis in Paris. He did in France, his PhD. Then Hausdorff, he has a great German mathematician. He wrote a monograph this year, and he discussed in more detail this distance between sets. So this is the Pompeu-Hausdorff or Hausdorff-Pompeu metric on the class of closed bounded sets, parts of X. So we are in a metric space, and the condition for multi-valued almost contraction is quite similar to the single-valued case. We have this H distance between Tx is a set, Ty is a set, and fixed point for a multi-valued, if you are not familiar, means X belongs to Tx, because Tx is a set. And these kind of multi-valued mappings are very important in applications. There were mentioned this important contribution by John Nash in economics, which are based on topological fixed point theorem, actually, not metrical fixed point theorem. And a group of Indian mathematicians, as I know, are from Andhra University, because Babu was, it was organized some years ago, a conference in his honor, and he invited me to speak. It was online. I don't know them in person, because at that time it was online. He wrote a paper, and instead of this condition, instead of the original condition for almost contraction, he used this. And this is a very interesting contribution, because if you remind, here in the original condition of almost contraction, we have L times dy Tx. And he put this minimum, and what is interesting, this condition includes both existence and uniqueness of the fixed point. So such a mapping in the single valued case includes both existence and uniqueness by including these four distances. And Madalina Păcurar in this paper this is in 2008, and in 2010 she showed that this condition is equivalent to the existence and uniqueness condition together. So this is the case, multi-valued case, I consider together with them. And here is the paper in 2007, and we can read together the theorem. The theorem, it's a very general one, but not the most general. So we have a complete metric space, T. It's a multi-valued delta L almost contraction in the sense I mentioned. This means there exists theta less than 1 and L positive, non-negative, such that we have this condition. And then we have existence, not uniqueness, and approximation result regarding the approximation of fixed points by an orbit. In that case, this sequence is constructed by taking xn plus 1 in the set T of xn. So all the time the sequence in this case is constructed in this way. So it's a kind of selection. And for this sequence, we have also, this is the a priori error estimate. We have first two points, x0 and x1, and this is called a posteriori error estimate. Why? This is very important in application. I'll have some application later in this week, but I want to take this opportunity to show you what is important this second error estimate. So we have the fixed point. We want to calculate it. We know that distance between xn and u, xn it's a sequence, is less than this h. H is not given here, but it's a number, something with theta. I do not remember now. And what does it mean? We want to approximate this in such a way that dxn u is less than epsilon. Epsilon is the error, the admissible error. So it's simple. We put here epsilon, and then we find that we'll stop our iteration algorithm when we have this inequality. Which is this? So what are we doing? We start with x0, we compute x1. We compute the distance is less than 1, we are done. Now we continue. Distance between x2 and x1 is satisfying this inequality, is done. And so on, we stop our process, let's say, at this step when this inequality is true. So this is very important from the point of application. Someone asked here, why is it important? Because in concrete examples, we have to compute this fixed point with a certain precision. So in order to have sure this precision, then we'll use this error estimate, a posteriori. A posteriori, it's a Latin. Latin is an antique language and means afterwards. And a priori means before. So we know afterwards, after doing some iteration, when to stop. And this is a priori because doing the same, doing hn 1 minus h dx0 x1 less than epsilon, then we got information about n. N will be greater than. Here we use logarithm, and then we'll get that we need to do n, let's say 100. This means we need 100 iterations. So we know from the beginning how many iterations to perform in order to get this approximation. And in the other case, we know just afterwards, after we compute the iterations. Okay, this is the record of interest for this paper. We can see more than 200 citations in Web of Science, more than 2,003 in Scopus, and more than 300 in the Google Scholar. So a very interesting paper. A lot of people use this condition. And I shall end with some other developments. I have shown you before some contraction conditions arising from Banach condition. Among them is the Chirich condition. I write once again it, because this is very important. dxy, dx, dy, dx, dy, and dx, dy, tx. This is the most general condition in the Rhodes classification of contractive condition. I mentioned this paper 1977. And what was my thought? Let's compare almost contraction conditions which is this one I write again. To Chirich condition, I said which one is more general. Of course, it was interesting to compare. I succeeded to find examples, and in this book I indicated there are examples to show that there are almost contractions which are not Chirich, and there are Chirich which are not almost contraction. That means they are, and there are mappings which are in both classes. So we are here. Almost contraction, Chirich contraction, and we have this situation. So my plan was, is it possible to unify this? This means to obtain a class which will include almost contractions and Chirich contraction because they are different. This would be similar how was done by Chirich-Reich rules when they unified Banach contractions and Cannon contractions. So they unified this. And I tried to do this. I said, okay, we'll have this. Instead of d of x, y, we put this quantity, which appears in Chirich contraction condition. And in this paper, General Constructive Fixed Points, I established some fixed point theorems. By chance, Chirich was asked to make a review. And he wrote me personally, I think there is something wrong in the proof. I feel it is not. So please read again, check the proof. It happens. You will see it happens. Sometimes we are quite sure the proof is correct from the beginning to the end, but sometimes one step, one argument is not solid, is not valid. So the same happened here. And the problem was coming from these two to deal with such a condition. You have seen an idea how to prove Zamfirescu fixed point theorem. The problem was when the maximum is this or the maximum is this. So there was the problem. There was needed another condition because such a mapping with M here does not have always a fixed point. This was the problem. So it was the case, and I constructed a very nice example, a simple example. This is important to mention. So we take what I said. Examples are fundamental. So we should prove that our results are effective, our results are real generalizations. So in the end, after several trials, I found this example. So it is easy to see that we define this map on the set of positive integers, non-negative integers, and in this way, this map is fixed point free, because n plus 1 equal n will be 1 equal 0. This is false, so no fixed point. But what is interesting, this map, it's a Chirich almost contraction. A Chirich almost contraction means we put m here, and the rest, the others remain the same. And okay, all the computations with alpha 1 over 2, L2, we can show this condition with m here is satisfied, but the map is fixed point free. So the theorem here, the main result here, is not correct. So I improved it, I corrected it, and the only way it is functioning is to put, instead of them, they are not good for the proof, so, but they are average. I'll speak next days about the role of average in mathematics. Average, what does it mean? We have something not very good, something very good, and if we do the average, what it results, it's quite good. And there was a famous Romanian mathematician, he did a joke with his students. The students did not understand the concept of average or mean. We say sometimes mean. Oh, she said, you don't understand what it means in mathematics, an average, a mean. He said, look, if you sit with this part of the body on a very hot machine, and with this side on ice, in the average it will be fine. So, this is the idea with the average. So the average is solving the problem. So if we put average of these two bad cases, then we get the result. And the result has been published in the same journal 1 year later, and this I called Chirich strong, because this condition with mi and 1 implies the condition with m. So I called strong Chirich. And I told in the break, during the break, to Professor Murti, I was in Belgrade, in Serbia. Chirich was in Belgrade. This is in Serbia. On the map with Romania, Serbia has a common border with Romania. Very good mathematicians in fixed point theory are there. And I was in Belgrade just to speak about Chirich almost contraction, because it was a tribute to him. He was very kind to say, look at the proof. This proof should have something. Okay. Now let's continue. All these results we discussed so far are for mappings which have this property we call self mappings. Self. But in applications, for example, if you want to apply a fixed point theorem to differential equations, it happens often we have to show how we deal with a differential equation. I wanted to show you some application to differential equation, to partial differential equation I published, but it was not placed in these lectures. So we have a differential equation, let's say initial value problem, and we know it is equivalent to a fixed point problem where t is an operator. And this operator is defined on a set, but it maps D in the whole space X. We have to prove that T of D actually has this property. This is a self-map. This means T is a self-map. But in many cases, we do not have this property. So in that case, we are put in the position to solve problems for non-self mappings. So we have to deal with such an application which does not fulfill this condition. And this is the case with non-self. I succeeded together with my collaborator, Madalina Păcurar, to treat this case, which is very, very interesting. And unfortunately, we published it, look, more than 10 years ago. We planned to have some applications, but we did not succeed. But because of the time. What is the fixed point theorem for non-self almost contraction? So we can work not in a metric space, but in a Banach space. We need linear structure of the space. You know, Banach fixed point theorem has been stated in a Banach space, in what we call now Banach space, because Banach did not call this space Banach. Afterwards, people called after his name. So we have a Banach space X. K is a non-empty closed subset of X, and T is a non-self almost contraction, means T is mapping the set K into the whole space X. And we know that we have this condition for almost contractions. If we introduce this property M comes from monotony. Because my co-author initial is M, some people ask, is coming from her name, and is not coming from her name, is coming from monotony. And this property is very important, because there is, in the proof, there is a similar case to the previous result I mentioned, and this is the property. I have one example, but I'll show you later this example on the slide. So this is the space X, this is the set K. So what happens for X is here, and property M, means that if we have such an X with Tx outside K, then we know that there is a Y here, the Y, the point on the border, the point with this property, not this one, sorry, because it should be in this way Y. There is such a point, such that Ty, it could be here, the distance between Y and Ty should be less than the distance between X and Tx. This is property M. And I'll show you a better example, a better draw. And secondly, if we have this condition, Rothe boundary condition, what does it mean? That the border, it's always mapped into K. So this means that any point from the border, this is why I put Ty here, because always points are mapped here. So all the time from the border we go inside. So in that case, we have the conclusion that T has a fixed point. If we are, as I mentioned, in the case of integral operator, Tx, this is a very strong tool for us, because we could solve differential equations or integral equations which do not satisfy these conditions. So we have, okay, I use K. T of K not included in K. We have this case covered. So this is the situation. So this is the set, this is the space X. This is the set K. And I took an X, and Tx is outside. And the requirement to have property M is that we should find amongst these points on the border, we have 3 in this case, at least one that distance between y and ty is less than tx and less than distance between x and tx. And this is property M. And because I insist to have always, when we establish or we pretend to be established a new result, we should provide an illustrative example to show our result, our extension, our generalization is effective. And this is the result. It is really nice. So we have here K is the real axis with the usual norm. K is the interval 0, 1, and T is this map. And you can see we are inside 0, 1 on this branch. We are inside of 0 on the interval 0, 1 on this branch, but we are outside at the middle of the interval of 0, 1. So we can check that this map is a non-self almost contractions with these constants. Look, 8. So I mentioned that an almost contraction is in general, in that case, we have greater than 1, while all the other fixed point theorems have less or at most equal to 1, is Hardy-Rogers fixed point theorem. And T satisfies property M. How? The border of this K, the border is 0 and 1, right? The point 0, 1. X1 over 2 is in K, but Tx is outside. So here it's 1 over 2. And okay, I cannot draw here is minus 1 somewhere. And the distance between between 0 and T of 0, which is, this is y, is 0, and is less than distance between over 2, 1 over 2, and minus 1, which is 3 over 2. So the property M is satisfied, and the Rothes boundary condition, I forgot to put here, we can check T of 0 is in our set K, and T of 1 is in our set K. So also Rothes boundary condition is satisfied. So we are done. This is a true generalization of other special. Now the last topic for today, it's just to give an idea on enriched almost contraction. I'll speak about enriched mappings in a separate lecture, but here I just want to show how we can continue to develop our new results. So in a paper which is not put here, I introduced the concept of enriched contraction. I'll give you very many details on this technique, maybe tomorrow or the day after tomorrow. I introduced the notion of enriched non-expansive mapping, but here I speak about enriched almost contraction. And what is this? we have a linear norm space. A mapping is an enriched almost contraction. If we can find a B, non-negative constant, a theta in this interval depending on B, and a positive, non-negative constant L, such that we have this inequality for all x and y. You can see immediately that if we take B equals 0, this term disappears, and we get exactly almost contractions, because this also disappears, B0. So these are almost contraction, but if we have L equals 0, we get enriched contraction, we get other classes of enriched enriched mappings that we studied. Sorry, this was published 1 year before, but I forgot to put a new situation. And this is an enriched contraction in Banach spaces, which is devoted to enriched Banach contractions, and this is enriched Canon in the third paper. This is how we could develop. And here it's again, let's speak once again. So we have almost contraction are here, and we introduced enriched almost contraction. And these are almost contraction. We pretend that this class is larger, but we have to prove. So we have to find here an object which is not here. And then we are done. So this means this set of mappings enriched almost contractions is larger than almost contraction. And then this means we have a benefit. We progressed in our work. By the way, because it was mentioned in the opening, maybe I'll have time to speak. Such a class of mappings I called unsaturated. This means we can enrich it. And if we cannot, if this class would be exactly the same, it will be saturated. This is another concept. I do hope I'll have time to speak. So this is the example. In that paper, we take X, this interval with the usual norm, and we define T in this way. So two branches, 1 minus 6 and 2 minus 6. It is immediately to see that 1 over 2 is a fixed point, because 1 over 2 will give this, and 1 is also, again, here, 2 minus 1 is a fixed point. So we have two fixed points. This is an enriched almost contraction for any theta in 0, 2, because B is 1, this is B. B is 1, theta is in the interval 0, B plus 1, and L is 3. And if someone wants to see this paper, I'll indicate later the exact paper. But this is not an almost contraction. We just show because it does not satisfy the almost contraction condition. Is not in any other class of enriched mappings I mentioned, and maybe I'll speak next days, is neither non-expansive nor quasi-non-expansive, is not enriched non-expansive, and so on. And this is indeed is not even enriched Chatterjee, then it is a very general class. So if these are almost contraction, look, Here are Banach, here is Cannon, here is Chatterjee, here is Zamfirescu includes all. There is Chirich, Strong, and so on. All are included here, and this class is overall. So it's comprising all these classes of mappings. I close with some other important developments. There is a very nice extension of this result. Tomonari Suzuki, it's a Japanese mathematician, and he succeeded to give result for Banach type contractions to show that they characterize the completeness of the matrix. So he published another paper and called these mappings almost contraction. He called Berinde mappings, and he succeeded to show that this constant I put here L can be a function of y. Very nice is his result, and he provided also an example showing that this class of almost contractions is more general than the usual almost contraction. There are many other developments. I don't insist on them, just to know that some other authors considered this kind of mappings even for non-expansive mappings on various kind of sets. Here is the group led by Sutep Swantai from Chiang Mai in Thailand. And many others, I don't insist on them. Just a few conclusions I would like to present. So, I discovered almost contractions searching for a proof. So this is very important. Sometimes I encourage my students to take a theorem and to look at its assumptions, to not look in any book how to prove it. Just to put in the left-hand side the assumptions, in the right-hand side the conclusion or the conclusions, and to try to find a bridge between them. And sometimes, if you are doing this, you should find new interesting results. I draw your attention on this name, Caristi. Professor Kamsi from USA, now he is in Emirates, will give a similar GIAN course in February in Aligarh. And he will speak about Caristi fixed point theorems. Caristi did such an approach. He used to be PhD student of this great mathematician, William Ard Kirk. And Kirk posed him the following question. Take Banach contraction principle and try to prove it in another way, not using the usual way Banach did by considering the sequence of successive approximations and prove that this sequence is Cauchy, is fundamental, then in a complete metric space is it convergent, then let's see x star its limit, and we prove then that the limit is a fixed point. So he tried another version and he introduced what is called now Caristi mapping. It's a more general version. It also includes, so here is Banach contraction principle, and here is Caristi. Okay, all the time while I was thinking, almost contractions are somehow here also. I had no time to, it's a challenge for you. I had no time to discuss what is common with Caristi and almost contraction and what is not. This proof is very nice of Caristi. By the way, Caristi, I know this story from an American mathematician. He left mathematics and he was very disappointed because he realized his theorem is very important. He submitted to a journal, and a great mathematician, I don't mention his name, he died. He was the reviewer. He realized this, it's a very important step. He realized it's a very important step. He was already a very famous mathematician. And he took the idea and he moved aside, I'll tell you, and proved a very important variational principle and published the paper before Caristi. Caristi's paper waited, I don't know, 2 or 3 years, and it was published after this paper, and this was really bad, really unfair thing, and Caristi left mathematics forever. He left mathematics, and as I know for this friend of mine from USA, he succeeded to contact Caristi. He was working, he was so disappointed because of that. He did some, how to say, psychological breakdown, and he was working in a farm, like a farmer, for a long time. And this mathematician, he succeeded to contact Caristi. This is an example of unfairness, unfortunately. Okay, so this is in connection to Caristi. Sometimes it is good to try to do this. So for any of these theorems, just try to see how another way, if possible, because sometimes we cannot see how to do. So, as I mentioned, I call this class of mappings weak contractions, and then I realized that there exist weak contractions, and in spite of the fact it includes a lot of contractive conditions I mentioned then, this condition is singular in the sense it ensures only existence and not uniqueness. And it is not a Picard mapping in the sense I mentioned, so it is a weakly Picard mention. So if we compare the theorem, fixed point theorem for almost contraction to Banach contraction principle, we see that the uniqueness is lost, but please look at the theorem I presented for almost contraction. All the others are present in the theorem from Banach contraction, except uniqueness. So this is its beautifulness. It's almost Banach contraction because it's how I said, it's a union of an infinite number or finite number of Banach contractions. And almost contractions have applications. Maybe I'll have time to present an application to functional equations. For non-self almost contractions, there are many interesting open problems. If someone is interested, should go to the original paper and consider developing in many other directions. Also, the idea of Suzuki with this L being not a constant but a function of y is also a possible research direction, very promising in my opinion. Okay, non-expansive mappings have in common something with this, and some people, you can see here, endpoints, this is generalized wherein the non-expansive mappings is related to almost contractions, but with this delta equal 1. So with non-expansive term there. And last, I want to cite, to quote from Suzuki. Suzuki, who is I do respect his results, he said that the concept of almost contraction has some mathematical beauty. So sometimes you ask, some of you ask about applications. Sometimes mathematics is done for its beautifulness. If we should have a look in the current mathematical research, we can say without any chance to be wrong that 80% is theoretical, pure research. We don't know exactly tomorrow what application will have these results, but I'm sure one day they will have an application. Maybe I'll tell you at the one of my lectures with applications about this very famous Fermat theorem in number theory. People at that time, another French mathematician, you should know about his name, Fourier. Fourier said, oh, these kind of results about number theory are not important for application. And nowadays, number theory is essential in cryptography. It's fundamental. All secrets are based on number theory. So sometimes it takes hundreds of years to find applications, sometimes sooner. I'm confident all these concepts in fixed point theory, but we have to work on it. We have to find application. I just heard in Delhi and Ghaziabad about applications of fixed point theory in machine learning. People are starting to work. I did myself some applications with some of my PhD students in image processing. There are many applications. I close. This is me 20 years ago, 21 actually. Can you believe? This means 20 years. So you can see here a piece of paper. At the moment, it was during the summer. This is a wooden house in the country. I have a summer house for spending time there in holidays. And with my wife, you have seen her now, and my two daughters, I knew at that moment this is an important concept. So here is distance between tx and ty less than alpha dx and y plus dy tx L. So exactly the condition. This is a historical picture. I love my daughter had the idea to make this picture 21 years ago. So this is almost contraction. Lot of work can be done related to this class of mappings. Just follow some of the indication I gave you. So we have to take a paper to read not in diagonal. By the way, when we grade papers for exam entrance to the university, I have a colleague of mine the same age. And always we grade in diagonal. Do you know what is in diagonal? Just have a look. Not noting this is 0.5 points. In the end, said this is 7 or 7.5. And when we meet together, we discuss what is your grade to this paper. 7.5. 7.5, exactly on diagonal. We do not read a paper in diagonal. We should work with pencil and paper. We read any concept. We go to its definition. We go to see some related concepts, some related results,
and be sure we understood all. This is what I tell to my students at this course, methodology of research. This is the way I applied almost always to when I read a paper carefully, then I found something to improve. I believe this. It was one mathematician, Romanian mathematician, he had no citations. His paper, no citations. This was 8 years ago, more than 8 years, very famous. And he was unhappy with this. And another mathematician, a colleague of him, said, no, your manner of writing a paper is wrong. You treat the problem completely. Please leave a small place for young people to go from there, a starting point. And he did this. So sometimes there are papers which are complete. So no chance to, but my belief is that in any paper, any result, always is it possible to make a connection or many connections, to take all together and to find something, a new way to conduct research work. So maybe I should stop here. If you have questions, put them now, please.
Hello. Anybody have questions regarding of this session?
If not, we can put next days.
Otherwise, you can note it also before starting the afternoon session. You can ask personally also if you have no.
This is not a conference, once again, as Professor Murthy said. It's an interactive course, interactive workshop. So you should ask any kind of question you think are important for you.
So you can note it out, if you have any questions, and you can ask after completion of this lunch break, and you can ask personally also. Otherwise, at any time of within the 5 days pattern. So I would like to pause our program for 1 hour. Working lunch is providing the besides of this room, and please go on take the lunch break. And after we will meet at 2 o'clock. Please be ready to meet here again, same place.
Fine? Okay. Many thanks. The same quality will be maintained. Don't worry. Not only for the first day, every day same quality. Quality wise you will not find any difference because I am a person who never compromises for quality. This is what my nature is. So after the lunch we are going to start our session, and with us is it tomorrow what we do is it possible those who have arrived from the outside, so can you introduce please the outside, from the outside please introduce yourself, name and place, university or college name please. Yes, pass.
Manjusha Gandhi, Associate Professor, Yashwantrao Chauhan College of Engineering, Nagpur.
Nanda Prasad Kushwaha, Associate Professor, Tribhuvan University, Nepal, PhD scholar. Thank you very much. Thank you, sir. I am Uday Kumar Khan from Nepal, Tribhuvan University, and I am PhD scholar and fixed point theory. Uday Kumar Khan, yes, sir. Yes, yes. My research in his domain, sir. Yes.
My name is Dilip Kumar Saha from Nepal, Tribhuvan University. I am under PhD scholar under the Ajit Kumar Chaudhary, sir. Yes, sir.
Rahul Mansotra, PhD scholar, University of Delhi. Supervisor, Anuradha Gupta.
Myself, T.K.S. Verma, PhD scholar at NIT Raipur. Dr. Devashish Mishra.
Yeah.
Mohammad Junaid, research scholar, Aligarh Muslim University, and I am a scholar of Dr. Javed Ali.
Right. You know Javed?
Yeah.
Myself, Ahmed Faraz. I am pursuing PhD from Aligarh Muslim University under the supervision of Dr. Javed Ali.
Very good.
My name is Anurag Verma. I am from the Government and PG College, Raipur. Our university is Pandit Ravi Shankar University. My supervisor is Dr. V.P. Tripathi, sir.
Sir, myself, Tushan Srivas. I am research scholar in GGU Bilaspur.
Our university. Okay.
I, Lakshmi Bichal, PhD scholar. My supervisor name Dr. Rashmi Kenwat. I am from Pune University under.
Your supervisor name?
Dr. Rashmi Kenwat.
Okay. Very good.
Namaste everyone.
So रिश्ते में तुम हमारी granddaughter
Namaste everyone. My name is Dr. Rashmi Kenwat. Completed my PhD under supervision Dr. P.P. Murthy, and now serving Anantara Pawar College of Engineering, Parvati, Pune. Thank you.
मेरे ख्याल से और कोई बचा के बाहर का कल बाकी लोगों को इंटरव्यू कल करेंगे, है ना? टाइम ज़्यादा वेस्ट नहीं करें, थोड़ा दे दीजिए माइक बाकी लोगों से बात करें.
Thank you. Please, I am not going to disappoint anyone because every day we have something to speak. Okay. So let me introduce Professor Veermani. I have, I think, a long association with Professor Veermani. He is more than my elder brother. Okay. So in that sense also, and for our Department of Mathematics, since my appointment over here 2007, when we have only MPhil students and MSc students along with PhD, but MPhil is more. So those days itself our students used to move to Madras, IIT, Math Science and Ramanujan Institute for their research paper collection or some visits. And he is a man behind that to entertain all our 10 MPhil students. Maybe this no one is right now here, those MPhil students. You visited? Okay, so you visited his house in IIT campus, right? So I think Dhananjay is there, so he will introduce. Actually, I was waiting for Dhananjay, he was a little bit delayed, so he will introduce. So this way, this professor is related to me, that how important personally, how important in fixed point theory. So let me say a very fine concept of fixed point theory. You know, after the investigation of fuzzy metric space, it was introduced. Okay, who introduced? You have to tell. Who introduced? No, fuzzy metric space. No, originally who introduced? Veeramani sir has given a tremendous modification in that definition. Right, sir?
Yeah.
Fuzzy metric space.
Not tremendous, some modification.
Yeah. So he has given a modification. What modification? I will request him to answer that and start his session. So that kind of concept which is still going on. Still going on. Whenever some people, they refer some other person, and most of the people for a particular cause, they have to refer Professor Veeramani. That's true. So that kind of fundamental result he has given. So now let me ask Dr. Dhananjay Gopal to introduce Professor Veeramani and start the lecture.
Yeah, thank you again.
Yeah, thank you, Professor.
So good afternoon to all of you. It's my pleasure to be here and to introduce such a great personality, and indeed thanks to Professor Murthy for this opportunity. As you know that Professor Veeramani retired from IIT Chennai, and he has you can find out in NPTEL his lecture on topology, and as Professor Murthy talk about this concept of fuzzy metric. And in fixed point theory, there is another way that is called the best proximity. So the sir introduced the best proximity, the idea of best proximity, and it is a very geometrical concept. Yeah, along with the curve, of course. But then I found also there is a very interesting, and still there are, maybe later on sir will tell about the idea which the Kerr-Kensar and other Rafa Spinola from Spain, they did many things, and then the renorming recently, the renorming the structure and the related fixed point. Sir told me sometime that there is still the open problem which I don't know whether how to solve it. So it's our pleasure to have here Professor Veeramani sir. So we welcome you for your lecture. Thank you so much.
Again, I think this is there. Again, thank you very much for both Professor Murthy, Professor Dhananjay Gopal, and all faculty members and all the students, research scholars. Yeah, will be more informal, and as Professor Murthy told, I will not go to fuzzy metric space, just I will tell the motivation for that, then we will go to fixed point theory. So, like fuzzy set, we have metric space we know. Matrix X which we are going to discuss, X comma D matrix space we know. It is like distance between X and Y cannot be negative, greater than or equal to 0, equal to 0 if and only if X equal to 0. D of xy need not be equal to D of yx. I come from X to Y one way, return direction I may take another way. But for many interesting results, we need that. We insist that d of xy equal to d of yx, and triangle. In a triangle, sum of two sides is greater than or equal to third side. That's why d of xy less than or equal to d of xz plus d of zy. Then we know that will induce a topology, and we know that again will come back. Then what is fuzzy metric is M for, in fact, Menger, who discussed about probably fixed number. It is just a fixed number. It will not change, but we are moving. Now that's what I say, distance between now x and Dhananjay Gopal, now we are very close. Degree of nearness is very close. To which degree we are close? One mean 100%, other than accordingly will, and the earlier thing they allowed 0. That means m of xy comma t allowed to take the value 0 also. But we found that to prove results from analysis, especially to generalize metric space, degree of nearness between x and y 0. That means what? No way they are like, what do you feel? Degree of nearness is 0. Now degree of nearness between x and y is very close. When it will be 1? Only when x equal to y. X equal to y 100%. Otherwise depends upon the time. We are moving. So if you move tomorrow or some other time, I will go far away. At time we are close and later we will move. So keeping that in mind, we introduce this is called degree of nearness between x and y with respect to t. We assume that always this is greater than 0, never 0. In the original thing they allowed 0. Then some properties, then in particular m of xy, every metric space will induce a quasi-metric and things like that. Anyhow, just to he told about that. This was introduced when I took my first student, George. In fact, he brought the Banach contraction theorem for quasi-metric space. Then what they use in one of the thing is, like this is very important. Suppose distance between xn plus p tends to 0 as n tends to infinity, p greater than or equal to 1. Can you say that it is a Cauchy sequence? Note that distance between xn and x suffix n plus p tends to 0 as n tends to infinity. Can you say that this such a xn is a Cauchy sequence? Yes or no? Anyone? Actually that's it. Many of you are MSc students, no? Correct? I want what? Okay. But you have to tell yes or no. Oh, camera may go. Normally my way of I will walk closer to students. Is it a Cauchy sequence? Think over and tell. If you are keep asking me something, do you think that it is a Cauchy sequence? Yes? Okay, I will give one. You are familiar with S1, we are defining a sequence. Sum of n terms. 1 plus 1 by 2 plus 1 by 3 plus 1 by n. N is fixed. S1 mean 1, S2 mean 1 plus 1 by 2, S3 1 plus 1 by 2 plus 1 by 3 like that. Okay? It's clear? Now what can you say about distance between Sn plus P and Sn? Sum of first n plus P term minus the remaining n term we are subtracting. So this will be equal to 1 upon n plus 1, n plus 2, 1 upon n plus P. What is here P? P does not tend to infinity. P is fixed. It may be 1, 2 or million, but it is fixed. So when n, how many terms are there? P terms. Each term tends to 0, then the sum, like by induction, xn tends to x, yn tends to y, then xn plus yn tends to x plus y like that by induction, we cannot write for when it is variable. So hence this will be satisfy this condition, whether it is a Cauchy sequence. What will happen if it is a Cauchy sequence? This is a sequence in where? Sequence in R. Every Cauchy sequence in R converges. If this partial sum converges means what? What is the series? Series converges if and only if sequence of partial sum converges. Sn is 1 plus 1 by 2 plus 1 by n. This is a sequence of partial sum of summation 1 upon n, the familiar harmonic series. So we know that that series diverges. In fact, why it diverges? Because again, see here itself, instead of p now take 2n minus sn here, then what is this? 1 by n plus 1, 1 by n plus 2 plus 1 by n plus 1. Okay? Is it tends to 0? Now n tends to infinity means 2n also tends to infinity. Now we cannot say that each tends to 0 correct, but sum is not finitely many term. The n also tends to infinity. In fact, this is greater than or equal to first term, greater than or equal to last term. Second term, like every term is greater than or equal to 1 by 2n, n plus n. How many terms are there? N by 2n. It is half. So it cannot be that epsilon is half. We cannot find any n naught. So that norm of Sn minus Sm less than epsilon. So what is important in Cauchy sequence is not the distance between consecutive term or distance between first term, some nth term and n plus 100 term. Distance between xn and xm approaches to 0 as n and m tends to infinity. So this is not a Cauchy sequence. That's why there they assume something what is called T norm. Using that, essentially it will come to like this. Then we modified even the Cauchy sequence, even in fuzzy sense we have to modify, and then we did some result, not in fixed point theory, only in basic result in analysis. Later I did not take any, all the remaining students all from fixed point theory, best proximity point theorem related to functional. Not any research level. Okay. Okay, now because as we told, we are going to review some concept from functional analysis, or you call it topology or metric spaces, which we need to understand some of the fixed point theorems. Okay? See, Professor Verende has given lot of result related to Banach contraction and that Picard's iteration. Essentially will come back later some other if necessary. All of us we are familiar with a function from close A, we will assume that A comma B belongs to R, A less than B, to self map. This we call it image of X. For X belongs to the domain, image also belongs to the domain. Such a map, codomain, codomain is same as domain. Such a map we call it self map. You might be familiar, even MSc level we do this result. Then it has then what is the conclusion? There exists if continuous, that is important, continuous map, then there exists this implied, then there exists at least one X in the domain, such that fx equal to x. How to prove this? Many of you know. Anyone? That's an interaction, as Professor Murthy and others told. It is not a conference. We try to understand the basic concept, then we can do some meaningful work. Why it is a continuity alone given? The domain is closed and bounded interval. Okay? Even still make it easier, we take even f from using once you prove the same idea. This is continuous. See, what we have is the square 0 to 1. What do you mean by the function has a fixed point? This is the diagonal is y equal to, okay, it is not a rectangle, square you take. X is 0, y 1, 1 1. Here 0 means 0 0. Yeah. So this is y equal to x. Y mean fx. So what do you mean by this function as a fixed point? See, think what will happen? F defined for every element in the domain. What can be f of 0? Suppose it can be either 0 or greater than 0. Suppose f of 0 is 0, then we are through. We are searching for a point 0 such that x, in this case x is 0. If f of 0 is 0, we are through. Similarly, f of 1 is 1, again we are through. There x is at least one point either 0 or 1, that is fixed. Suppose both are not true, that means what? F at 0 is some positive number, f at 1 is less than that, the function is a continuous function. Using topological idea, not our very advanced topology, very simple, R to R, metric space only. A metric fixed point theorem we are telling, that's why only. What can you say about interval related to? You are familiar, no? What are the connected set in metric space? R is a metric space. D of xy equal to mod x minus y, usual metric. Okay, that will define a topology, forget about that. We can define open set. And then what is the relation between connected set and interval in R? Anyone? Actually MSc student. Intervals are connected and they are the only connected set. Okay, that we can prove using LUB axiom or like that. So, in fact, what is some theorem which we are very familiar? The name is, what is the name of that theorem? Some theorem using that name will not talk about connected or anything. Just will say that some mediate theorem, intermediate value theorem. Intermediate value theorem, because ultimately what we want is fx minus, we want to find at least one x for which this is 0, fx at least one x, so that fx equal to x. Okay, now that's this we call it G from where to where? G is a domain is close 0, 1 to even R. Okay, we don't doubt G at 0, f at 0. Minus this. Okay. What can you say about this? At which point fx is always greater than or equal to g. It is in closed interval 0, 1. x is in closed interval 0, 1. Then, I mean, we will see that at one point it is, here we are assuming that fx is positive this and fx is less than 1, okay, that we do. At one point it is positive, at one point it is negative, then it takes some any value in between. That means we will find an x between f of 0 and f of 1 so that fx is 0. So that is simple exercise you do. Okay. Now, in fact, this is what this will do for any interval, need not be where we use the, suppose, can we use, prove this theorem for open interval, even, is it where we use the closeness, I mean a equal to 0, b equal to 1. We need that f of 0 and f of 1. So, similarly f of a and f of b. Say, otherwise, continuous image of this is also connected set. Image is connected. Connected mean again interval. See, that should again, codomain it is an interval. If we take a point in between, then there exists a pre-image. So that, okay, this will, you can go through, if you have doubt you can ask later. So, you can give also example, f of open interval, it will not work, okay. Next is, it is continuous. What is more important here is, the domain is closed bounded interval, closed interval, that we call it, later when you go to functional analysis, what you call interval mean, if we take any point x and y, all the point in between. What is the point in between? X comma y belongs to a, then all, what is the point in between? 1 minus t x plus t time y. It is like telling that at time 0 you are at x, you are travelling, at time 1 you will reach y, okay. So, this again should belongs to a for all 0 less than or equal to t less than or equal to 1. If a set has that property, of course we have, if you want you can assume a or r power n, subset of r power n or any vector space, okay. What we call this? If a has this property, we call it, it is a convex set. Say in intervals or convex set. So, because when you go to r power n, we do not have interval. See, interval means we define the order relation. See, closed interval a comma b, set of all x in R, say that a less than or equal to x less than or equal to, this order relation is there. If we are in R2 itself, we do not have. More generally, any vector space or nonlinear space we do not have, but we can define the that we call it convex combination of x and y, set of all. I mean this what even we define this itself for a comma b belongs to a vector space, then we define this is set of all 1 minus t times a plus t times b, say that 0 less than or equal to t less than or equal to 1. So, this because we have addition, scalar multiplication all in a vector space. So, define convex set, this is sufficient. In fact, you will see that every convex set in a R power n or nonlinear space, they are all connected set. In fact, it is pathwise connected. Path means, see that's what I am travelling from xy any two element. xy belongs to the topological space x. If you don't like topology, take metric space. Okay? Then we should be able to find a continuous function more generally from any closed interval a comma b, a less than b, or in particular enough to consider f from closed interval 0 comma 1 to that vector topological space X, such that at time 0 you are at X, at time 1 you are at Y. There is a continuous function satisfying the condition that f at 0 equal to X, f at 1 equal to Y. Then that we call it a curve or path joining X and Y. If for every pair XY, if there is a path, then we say it is pathwise connected. That's what all the convex set, because not in a, can we define vectors? In a vector space, convex set we can define. Can we talk about connected set in a vector space? Yes or no? Mainly I want from MSc student. Convex set we can define. Closed interval A comma B. Pardon? How we define connected? No separation. A topological space is connected means the only set, the empty set and capital X are both the empty set and X are both open and closed. They are the only sets which are both open and closed. That's a disconnected means there is a separation. Anything you can assume that even closed 0, anything, even if we can, there is a separation. Pardon? Yes? Oh, yes or no? In R it is not open. So what is your answer? Not open. So what is your answer? You are correct. 100% correct, you got the idea. But still little more. What is our space? Our X is closed interval 0, 1, union closed interval 2, 3. Our topologic space is not R. R is, we are restricting our space to closed 0, 1, union closed interval 2, 3. That's in the subspace we call it. Here the sets are open. Each point is an interior point. Suppose if we take closed interval 0, 1, 2, 3. 1 is 0 is an interior point. Why? Interior point means there should exist a neighborhood, center at X, radius some epsilon or R. So center at interval 2, 3. Then we have to talk about, we don't know, our world is capital X. Our world is not X, R. So we have to consider what is the open interval here. Open interval, or you call it ball center at X, radius R, mean those elements in our space. We should not go outside our world. So, y in X, as the distance between y and X is less than R. First of all, y should be in X. That means we won't get element from left side. So closed interval 0, R, X is 0. This will be a open set or neighborhood of 0 in this space. So hence 0 is an interior point. Similarly, even it is here 2, mean this side, or here 2, some 3 minus epsilon 2, we cannot go beyond 3. So like that. So this, okay, at least MSc student you should know some basic thing. Okay. Okay, next question. Exercise is, you give proper proof f continuous function from closed interval a, b to closed interval a, b, then it has a fixed point. There is at least one. Even it can be every point also identity function, fx equal to x. It is not only continuous, it is isometry. What do you call it, isometry? In metric space? Isometry. Distance between fx and fy equal to distance between x, y. Here fx equal to x, fy equal to y. So distance between fx, fy equal to distance between x. It is an isometry, not only continuous, very strong condition. Still it need not have it has a fixed point provided it is a closed unbounded interval. For example, you take this, just a bounded is okay, it is not very strong if you feel. Suppose this is standard example. What is this set? It is a convex set. It is an interval. It is closed and what is not there? Bounded is not there. I mean closed and bounded in R means something we call it compact. It is a closed convex set or closed interval. Will it have a fixed point? Can you give an example from closed interval 1 comma infinity to closed interval 1 comma infinity and give some function which does not have any fixed point? Quite naturally is what? No fixed point means the easiest example is what type of map you can think of? Here you take any x in the domain, close 0, open infinity, you can go right side any, no restriction. See, if you are closed interval 0 comma 1, you cannot go beyond 1. Now x anywhere, then you can go anywhere right side. So x should not be equal to fx. So what will be the natural map? Very good. X equal to any translation. Fx equal to x plus 1, x plus 2 or fx equal to x plus a greater than 0. So still it is isometry. Still again distance fx or non-expansive we call it later will come. It need not have a fixed point. Still more generally, sir, morning all you have seen that distance between x is complete metric space, Banach contraction. Distance between fx, fy, what is that? Less than or equal to k times distance between xy, where 0 less than or equal to strictly less than 1 for all xy. Then it has a fixed point, that is unique. So this is strictly less than. Can we write this? Yes or no? You should be very careful while answering. Can we write k times d of xy because k less than 1? Can we write k of t of xy less than? No. Saying no is research. Yeah. Why we cannot say? Suppose d of xy is 0, x equal to y. X equal to y means d of xy is 0. Then k times d of xy also 0, whatever may be the k. Then less than d of xy means x equal to d of xy is 0, 0 less than 0. So contradiction. That's why we have to impose the additional condition that x not equal to y. That we call it contractive map. Okay? See, this is for all xy in this, with this additional condition x not equal to y. Here also, in fact this map is a nice map. This satisfies this condition. Again exercise. Distance between fx, fy strictly less than distance between x comma y for all xy in closed interval 1 comma infinity, x not equal to y. What is fx? I have written, consider this map, I did not write the map, consider this map, fx, I will write, fx equal to, define, here I have written, define this, f defined as fx equal to, see x plus 1 by x, that's it, 0 should not be there, then we cannot write 1 by x. X is positive, you have taken 1, if you want you take 2, 3, anything. Okay? Then it is not translation now, almost like x plus some positive number. Okay? Then x cannot be equal to fx. Fx means x plus 1 by x, equal to x means 1 by x is 0, 1 by x non-zero. no fixed point. Then exercise, symbol X, that I will give a lot of exercise. D of Fx, Fy less than distance between xy for all xy in the domain x not equal to y. See, even though not just complete metric space, closed subset of a complete metric space is complete. Okay, closed interval 1 comma infinity is a complete metric space. Domain is complete, but it is a self map. It is not a contraction. But still, what we can get is for each x, we can get that k depends upon xy. K depends upon x not equal to y. We can find a k. I mean, this x not equal to y means we can define d of xy. We can find some fx, fy less than or equal to k depends upon xy time xy. This is less than 1. But what is? It varies. If we vary xy, then x, it may go to infinity also, sorry, 1 also. Okay? So that's why this is the standard example of a complete metric space. You cannot replace contraction by even contractive. But that case we need a very strong condition, namely compact metric space. F from capital X to capital X, X is a compact metric space. F from X to X map contractive, that means distance between Fx, Fy strictly less than distance between xy, x not equal to y. Then, I mean, essentially we know that x goes to distance between x and tx. It is a continuous function on a compact set attains its minimum. So using that we can prove it. Later we will see. Now, okay, are you MSc student? What is the, when you complete metric space, what are the complete metric spaces you know? Because everywhere we use first complete metric space for Banach contraction theorem or anything, or whatever mornings are discussed. Everywhere we need complete. Because iteratively we define a sequence section, that sequence is a Cauchy sequence, then it converges. No difference between Cauchy sequence and convergent sequence. What are the example you know? Complete metric space. The simple example. R. I want the proof from one of you. I will give a simple exercise. How you prove? There are many ways. Because R is complete means immediately R power 2, R power n, even any space, LP space, EOP, everywhere you will use that R only complete. Other some additional, some extra thing. How to prove R is complete? Let us start with a, how to start at least? Let Xn be a, okay, again I will incomplete only, I will give the, we want to prove that R, what is metric? D of xy equal to mod x minus y for all xy belongs to R. We want to prove that this is complete. And in this we can quickly, because there is some nice simple proof. See, which anyone you tell, I will give you, if you know this, if you tell some proof, I will see whether I can give another proof. If you don't tell me, I will not give that, I can give whatever I know. So you tell what proof you know. R is complete, how you will prove? Anyone? You have not seen the proof? Maybe first MSc, BSc now, you are in the third semester, you don't remember. Or start with a Cauchy sequence. Convergence mean what? First start with what is the definition of convergence of a sequence here in R. What do you mean by convergence of a sequence? Give any epsilon. this I normally just for fun I will ask what is epsilon or what is the, you should not ask such a question which is expert will not like. What is the definition of epsilon? Huh? Very small. Can you say it is the closer to zero? What do you mean by closer to zero? Definition. Mathematics you cannot escape. Closer to, I am closer to Mr. Dhananjay Kobal. I cannot, I have to tell, define what is the definition of closer. X belongs to A closer, we have some definition like that. What do you mean by that? It is the smallest, positive smallest. I wanted that answer to tease you. Is it possible to get a smallest positive number? Whether smallest positive number exists? Huh? No. Positive number, that positive number is such that you give any other positive number, that positive number is less than any other positive number, less than or equal to. It may be equal. Is it possible? There is nothing like, suppose it is a positive number, you call it epsilon or alpha. Alpha is the smallest positive number, means first alpha positive. Next it is alpha positive, means what can you say about alpha by 2? Again positive, alpha by 100, alpha by million, everything is positive, nothing like smallest. Smallest positive number, nobody is small in the world. I mean, see, we have a positive number, only thing we know it is greater than 0, that's all. That we call it epsilon, that is depends upon our need, that we call it error. Again this I give some, let us say we want to make a golden ring, nice ring, I want exactly they can measure. Some goldsmith, first day is working, then the total length, or you call it radius, total length becomes 0.9. First day, that means first day it works 0.9. Now you can guess second day, say 0.99. So we call it x1 0.9, x2 0.99, x3 99 like that. Now we know that. Okay. Now what is the error? What is our goal? To reach 1 perfect. The first day if you work, actual value 1, approximate value is 0.9. What is the error? Error is 0.1. Okay. Second day 0.1 like that. So depends upon our need. If you say that our error should not be greater than 0.1, should strictly less than 0.1 means even first day will not work. At least we have to go for second day. Some other engineering, some very important things, aircraft or somewhere, even 0.999 100 times, the error 0.000 something, but still that may cause a damage. Then that case will fix the error is less than 0.00 like that. That's a depends upon our need, we fix epsilon. Epsilon is what? Just a positive number. Epsilon may be 100 also. So, yeah. Suppose your pocket money, say research scholar or MS student, parents are giving pocket money. You will ask pocket money is 0.01 rupees, you will not like, no? At least you tell them, okay, minimum 100 rupees you have to give. There epsilon may be, and it depends upon, just to say that, that's why we fix epsilon is positive. That is more important for engineers than mathematicians. The error. That's why numerical analysis, anywhere, convergence. And that's what are iterative. We get some distance between xn and the fixed point x naught less than or equal to some k power n divided by 1 minus k. K power n tends to 0. that can be made less than epsilon for suitable large n. Is clear? So, xn converges, that's why we say that first we talk about xn converges to x in R. If and only if, for, please don't avoid to write however small it may be. No restriction, epsilon is positive number. For epsilon, then there exists a stage, what we call it? There exists a stage, that we call it n epsilon. Just to say, if you want, you can call it n naught or some other k, such that distance between xn and xn naught less than epsilon for all n greater than or equal to n of epsilon. Is it correct? Cauchy sequence. Sorry, this is for Cauchy sequence. Okay, convergence is, first I will define xn Cauchy, if and only if, a convergence will come later. This correct or not correct? Are you familiar? We are not telling that mod xn minus xm less than epsilon for all nm greater than or equal to some stage. We have fixed one n, like telling mod xn minus x naught instead of n naught, because it varies. If we change the epsilon, same n naught will not work. Is correct? Yes or no? This is very, because you can just triangle inequality instead of epsilon, you can write epsilon by 2, epsilon positive means epsilon by 2, then we can write xn minus xm less than or equal to xn, xn of epsilon plus xn of epsilon comma xn. So that's why here xn, xn and xm this, symmetry is there. Each is less than epsilon by 2 means this is true for all n greater than or equal to n naught. This is equivalent, symbol, I mean essentially same thing, Cauchy sequence if and only if this. Now, using this definition of Cauchy sequence, and have you heard about least upper bound axiom? In analysis that is very important. Completeness axiom also they call it. What is LUB axiom? LUB axiom. Not heard? Supremum infimum. But what is the supremum infimum correct? But what is the statement? It is an axiom, not a theorem. Later, that's what Professor Murthy also suggested me. So discuss about Jones' lemma. Because that we are going to use in a fixed point theorem. This also we are going to use, completeness. At least basic thing we should know. First lecture today, basic thing, then tomorrow onwards, if time permits, today itself will start or tomorrow. What is? Every closed and bounded set is? Correct. Every closed and bounded set has supremum, but that is LUB axiom. You can prove using that if a non-empty subset of R, non-empty is very important, non-empty, we cannot just, okay, doesn't matter, empty only I removed, you reduce 1 mark and give the, out of 10, you reduce 1 mark, I have missed non-empty. Non-empty is important. Capital A non-empty subset of R, and it is on, we are going this right side, and you should not keep going like closed one open infinity, no upper bound. What is upper bound? An element alpha, see again I will recall, A is any non-empty subset of R. A non-empty subset of R, alpha belongs to R. Note that need not be in A, it may be in A, because A is also a subset of R. Alpha belongs to, we don't insist that alpha should be in A. then alpha is said to be on upper bound for A. When we say if and only if, see A is here, alpha is somewhere, we know the real line. All the x in A should be left side. That means including that, if and only if x less than or equal to alpha for all x in A, then we say that alpha is an upper bound. Every set will have an upper bound. Any subset of R has an upper bound? No. How to prove? We can say we feel that alpha plus 1 also upper bound. X less than or equal to alpha means less than or equal to alpha plus 1, alpha plus 2. In particular, x less than or equal to beta for any beta greater than or equal to alpha. Infinitely many upper bound. Among the upper bound, take the least. So, what is the least upper bound? First of all, it should be an upper bound. Alpha is called least upper bound means first condition, alpha upper bound. Second, beta is an upper bound for A imply alpha less than or equal to beta. Okay. Then what is LUB axiom say is, if a non-empty subset has an upper bound, then it will have least upper bound. That is LUB axiom. Now we can prove that similarly, if a non-empty subset has a lower bound, then it will have greatest lower bound. That we call it infimum, least upper bound, supremum, like that. Okay. This is clear. You feel free. Don't worry about fixed point theory. That in between also we will talk about fixed point theory only. But basic thing first be familiar. Is clear? What will happen if you allow empty set? A is a subset of B. Alpha is an upper bound for B. Will it imply alpha is an upper bound for smaller set? Closed one, open interval, closed interval 1 comma 2. 2 is an upper bound. Okay. Anything greater than also upper bound. If you take a subset, closed interval 0 comma half, x belongs to subset means x will be in the larger set. Already larger set itself, every x less than or equal to alpha. I mean subset has an upper bound, superset. Larger set has an upper bound means any set subset of that should have an upper bound. Okay. Suppose if you allow empty set, okay, empty set has a, according to this empty set should have an upper bound. Okay. Then what should be the least upper bound? Minus infinity. Is that correct? Is it a real number? We want a upper bound, least upper bound, they are all in R, set of real number. We want in R, we don't go to extended real line. When you do Messer theory, you need extended real line. Now we are in R, not extended real line. So our least upper bound are all in R. Okay. So then y is telling in minus infinity means every real number is a empty set is subset of singleton alpha. That means greatest lower bound is less than or equal to alpha for all alpha. That means what is the real number less than or equal to every number is no number. Minus infinity is not a real number. That's why we'll taking why some theorem we assume that non-empty. Why we give importance to non-empty. Don't just say that it doesn't matter. Okay, infinity means something why ask the question. So like this teacher, nice teacher is there, don't leave him. Then he will explain. If you don't ask, we may not realize that you need that. So if you ask things, naturally, if not immediately, we will also discuss next day or after few days, we will come and answer. Okay, it's clear? Now, convergence is, that's the same thing. Xn is a sequence in R. Again, this we will not spend more time. For epsilon greater than 0, there exists a stage n here, there exists n of epsilon, a natural number such that mod xn minus x is less than epsilon for all n greater than or equal to n of epsilon. That is why it is in the neighborhood. Whatever may be the neighborhood, this we call it in R, open interval x plus epsilon comma x minus epsilon, epsilon positive, it is a neighborhood of x. So how many points may be outside? N greater than or equal to n naught mean all are inside. N less than or equal to n naught mean we do not know. It may be inside or outside. What is important is whenever n greater than or equal to that positive integer n of epsilon, then all the xn should belongs to this neighborhood. That's however small, the neighborhood may be still very small. We cannot write, it may be still very small. Still only finitely many members are allowed, except finitely many all are inside. Okay. Now we will use Cauchy sequence. I will give the outline. Yeah, otherwise we will have only all the 5 days only basic thing. Okay. Now what is given? Xn Cauchy sequence. In fact, motivation is simple. What is our aim? To find a where it converges. You have to find a x. If at all x we feel that it is a Cauchy sequence mean, hence for again for epsilon positive, there exists a positive integer, n set of natural numbers such that mod xn minus xn of epsilon is less than epsilon. For what n? For all n greater than or equal to n of epsilon. That means, see, it is almost the x is closer to xn of epsilon. That is fixed. For a given epsilon, there is a n of epsilon. The after n greater than or equal to n naught, the difference between xn and the n x suffix n of epsilon is less than epsilon. It may be 0.00001. I mean, some practical purpose, that much error is we can tolerate. Then we can take that as good as that is our result. Okay. That's why we need numerical analysis also. So that is, hence this implies minus epsilon less than xn minus xn of epsilon less than epsilon for all n. Now we can add both sides, that is xn of epsilon minus epsilon less than xn less than xn of epsilon plus epsilon. Then for all n, see, that means what will happen? If epsilon tends to 0, the interval will shrink. See, x will be where? If it converges means x will be between xn of epsilon minus epsilon and xn of epsilon plus epsilon. X will be there only. That means what? X will be greater than or equal to x of n of epsilon minus epsilon, and the same time x will be less than or equal to x of n of epsilon plus epsilon. Keeping this in mind, we define this set. Now take or define. So what we can feel x should be? Go from left side to where you have to find the point x. Either you can go from left to right or right to left. Suppose we are starting from left. So where x suffix set of all x suffix n of epsilon minus epsilon. This set is for each epsilon there is a stage n of epsilon. Then for every n there is xn. From there minus epsilon. This is a non-empty set. Okay. Now this set as an what you feel which is an upper bound. In fact this varies. Fix epsilon 1 positive. Then prove that immediate. Prove that x n of epsilon minus epsilon less than or equal to x n of epsilon 1 plus epsilon 1 for all epsilon positive. See here, for a given epsilon there x n of epsilon. Here epsilon 1. For that also only one way, now don't write the second. Epsilon is arbitrary, fixed. Any epsilon, this is fixed. Then we will have this. That means this will be less than or equal to x n of epsilon 1 plus epsilon for every element. This is an element in S. So what is an upper bound for the set S? Upper bound for S is every element. What is an element in S mean? For an epsilon positive, x suffix n of epsilon minus epsilon. That is an element in S. For each epsilon there is x n of epsilon minus epsilon. Each element is less than or equal to, see, first will be this condition when this will be true whenever n greater than or equal to n of epsilon. This will be true for all n greater than or equal to, at a time you fix one epsilon but arbitrary. Here you have fixed. Now we can take the both we want. N should be greater than or equal to n of epsilon as well as n of epsilon 1 also, our usual way. Take the we want that x n of epsilon minus epsilon less than some alpha. Also we have on xn is, this we have. See, this will be from here. This will be from here we got this. This inequality will be true whenever n greater than or equal to n of epsilon. This will be true whenever n greater than or equal to n of epsilon 1. So you choose here, at a time epsilon is fixed, epsilon 1 also fixed. Then we can take the maximum of n of epsilon and n of epsilon 1 or even sum. Then this inequality will be true. Hence not only what is great, the important thing is for every epsilon 1 is fixed but arbitrary. Whatever may be the epsilon, x n of epsilon plus epsilon is an upper bound for S. Okay. Now use that one to prove that it has an upper bound, hence by LUB axiom the set S has a least upper bound, say x. X least upper bound means what? X is least upper bound. For any epsilon, it is one element of S. This will be less than or equal to because an upper bound. Okay? It is upper bound. Among the upper bound, it is least. What can you say about x n of epsilon plus epsilon? That is another upper bound. This is least. So least will be less than or equal to this. So hence we will get modulus of x n of epsilon minus x is less than or equal to epsilon. Similarly, sorry, you have this mod xn, already we have this mod xn minus xn of epsilon. Instead of epsilon we can write epsilon by 2 also. Then triangle inequality, mod xn less than epsilon, xn minus x. We will write this is now mod xn minus x less than or equal to xn minus xn of epsilon plus xn of epsilon minus x. This will be less than epsilon or epsilon by 2. This and this will be by the definition of Cauchy sequence. Hence that will, they only on outline, but I don't want to spend so much time. You please, these 5 days, at least today and tomorrow you try. If you have doubt, you are most welcome to come and discuss. I will explain. Okay? We are not using anything other than LUB axiom. In a natural way, x is sandwiched between xn of epsilon minus epsilon and xn of epsilon plus epsilon for every epsilon. That's why you take the x should be, we know idea where it should be. So that will give you a, normally what many different way will prove. One way is every Cauchy sequence is bounded. Once is a bounded sequence, then what? Every bounded sequence in R has a subsequence which converges to an element. Again, for that you need a LUB axiom. Again, a Cauchy sequence has a subsequence which converges, then the original sequence itself converges. All these things you will have to use. Here we don't use anything, just only the definition of Cauchy sequence and LUB axiom. And LUB axiom we cannot avoid. Completeness axiom, even to prove other results like Bolzano-Weierstrass theorem, other things. Okay? Using these now, you will better understand now R power n complete or L infinity. What is L infinity? All the bounded sequences, real velocity, complex also allowed, set up all bounded sequences. Then distance between x, y, supremum of x is one sequence xn, y another sequence yn. Then distance between x, y, supremum of mod xn minus yn. When we can write supremum? If the seek set mod xn minus yn should have an upper bound. First you have to verify, we should not write supremum without knowing whether it has an upper bound or not. First verify that using bounded. Mod xn minus yn less than or equal to mod xn plus mod yn. Mod xn is bounded, less than or equal to alpha. Mod yn is bounded, less than or equal to some other beta. Hence mod xn minus yn less than or equal to some alpha plus beta. It has an upper bound, hence supremum exists and it is real number, not extended real number, because d of xy should be a real number. It should not be infinity. Okay? So those things you can use. In between, if you want to have some break, you can, the organizer can tell. I mean, if you want to come back afterwards, we can come back. Now or after some time? After a few minutes. Whenever you want, you please tell. Okay. Maybe whatever we discuss, I will ask some of you tomorrow. So, like f from close AB to close AB, continuous means it has a fixed point. That is trivial in the sense that nothing but intermediate value theorem. Nothing but continuous image of a connected set is connected. That is what, to prove intermediate value theorem, you need this. Continuous image of connected set is connected. School level also we used to use BSc, that time we will not tell connected all those things. Easy to tell intermediate value theorem, because that is we use for solving equations everywhere, finding the root. There is a one root, one negative, one positive, there is a root, all those things. Well, not, but essentially what we need is continuous image of a connected set is connected. But the same thing even from R to R2, K a non-empty, closed, bounded, not interval. In place of interval, what we should have? K a non-empty, closed interval A comma B, closed set, non-empty, closed, bounded, interval. In place of interval, R2, Rn, what we will use? Yeah, convex. See, any 2 point can be joined. Set of all 1 minus t time x plus t time y, 0 less than or equal to t less than or equal to 1, that is nothing but line joining x and y, even in vector space we call it. So that we can define in any vector space. Thus a later we will give example, simple example is every convex set in any non-linear space or Rn is pathwise connected and hence connected. Okay? But if it is a K non-empty, closed, bounded, convex set, F from K to K, continuous, yes, then there exists x in K such that Fx equal to x. This is highly non-trivial. That is a morning also. It was proved by Prower in 1910, I think, yeah, 1910 or 1910, I think. If it is a unit ball R power n, set of all x such that norm x less than or equal to 1, that is our K. F continuous function from K to K, then it has a fixed point. There you need algebraic topology or combinatoric or advanced calculus, I mean non-trivial proof. So there are even very recently also some people have given some different proof. Giving any something interesting proof will be known result but somewhat simple. It will be always, it is not easy. That is topological idea, algebraic topology or other ideas. Okay, that, but at least we should know the statement. K, not only that, later somewhere in 1930, Sauder, Sir Manning mentioned about Sauder. If K is a non-empty, closed, bounded in Rn is compact. Infinite dimensional case, closed and bounded set need not be compact. So we need compact. K a non-empty, compact, convex subset of a Banach space. Okay, Banach space means every Cauchy sequence in X converges to an element in that space. It is complete metric space. Non-linear space, which is as a metric space, d of xy equal to norm of x minus y, is a complete metric space. Okay. Then these are non-trivial again, but use Prower's theorem to prove Sauder fixed point theorem. K is a compact convex set, F from K to K, always compact or non-empty. Otherwise, to define a function, domain should be non-empty. Then it has a fixed point. Again, that is highly non-trivial. I mean, so using Sauder, at least we can understand. Prower is still more involved, and later we will see either you can use Prower fixed point theorem or later what is called each image of each point is a set. See, suppose I am defining closed 0 open infinity. F, I will call it T, just image of x equal to closed interval 0 comma s. That means what? What is T of half? Closed interval 0 to half. T of 1 is like that. Image of each point is a non-empty set. That's what morning Professor Berende also mentioned. K is a compact convex set. T from K to K multi-valued map. So there what is called upper semi-continuous, later will come. Inverse image of closed set is closed. That is called upper semi-continuous. Then that case there exists a point x in K such that x, not x equal to Tx, x belongs to Tx. Then we can use that theorem to prove what is called Nash equilibrium point. That is one of the lecture I am planning to give the proof, motivation to what is the importance of multivalued fixed point theorem. We will not prove Kakutani fixed point theorem or this, at least without anything. What is the natural way to get an equilibrium point? That was introduced by John Knox somewhere in 51 or 50, yeah, somewhere in, that's what the man, there was a beautiful mind movie in English. He was a student like you, 21 years or so. That time he introduced, pardon? I think it's 52. Maybe 50, around 51, 52 in that period. So he introduced that concept, that's what as I told, 2 pages. Later he, somewhere late 90s, somewhere in later, he received Nobel Prize. This was one of the important result, his major contribution, that is application of fixed point theorem. So like that many interesting applications are there. Of course all of us familiar with integral equation, differential equation, there are something called invariance of space problem and many eigenvalue, eigenvector, many things. So I will at least discuss this equilibrium point. Okay? Okay, we will have tea. 15 minutes, okay, fine. That is good for, we are right from morning 9 o'clock today. You can have a relaxed time 15 minutes along with the tea.
आदर्श आदर्श सर को लगाओ, ये बिल्कुल तुम्हारा काम है। आदर्श का और वो रश्मि, वो कहाँ गई हमारी लड़की, दिखी नहीं रही। ये तुम लोग थोड़ा मेरा भी मेरे आंखों सामने आकर कहीं भी तुम देखता ही नहीं हो, और वो लड़कियाँ दोनों, तुम और स्मृति थोड़ा सामने आकर कुछ काम बता सकता हूँ तुमको।
अच्छा बोल के देखिए। हाँ ऑलराइट।
ये इसको नहीं मिले होंगे आप, उमा को तो जानते हो आप लोग, हमारी रिसर्च स्कॉलर है, नहीं सभी लोग। एक रश्मि है, रश्मि खड़ी हो जाओ, ये मेरी फर्स्ट रिसर्च स्कॉलर है, ये पूना में है, वहाँ के कॉलेज में काम करती है, ठीक है। और बाकी बहुत सारे स्टूडेंट्स एमएससी के भी हैं, और ये 2 रिसर्च स्कॉलर्स और भी हैं। So once again you please settle down. From tomorrow sharp 10 o'clock the class will start. Okay, the interaction session will start sharp 10 o'clock. So I will request the transport in charge to settle the bus at 9:30 over there, that you can settle down here before 10. At least it should be 10 minutes to 10 you settle down here, and after that we start sharp 10 o'clock. And Professor Birende is occupied with lot of national accreditation issues. That's why he is very, very busy. So you make his time, okay, properly, make use of it. Of course, Professor is also available with us, whatever it may be, okay. And I request the Professor to give them some sort of work that they should think the whole night. Whole night, at least after the 6 hours rest. 6 hours is more than enough for you. You are the research scholar, 20 plus, no one is less than 20. So 20 plus 6 hours sleep is excellent sleep. More than that becomes laziness. These 5 days you follow this pattern. Okay? And I have seen yesterday some of my young friends, they wanted to move outside. I have taken some of them also, right? So you got the tea yesterday night. Okay, I am thankful, otherwise you would have scolded me like anything. So I think Professor discussed about the that introductory part very nicely. He explained about the convergence part, because many times it is very difficult to understand what exactly the convergence we do mean. Convergence we understand, but sometimes we fail to understand the Cauchiness. That is very, because the Cauchy construction is a little bit different from the convergence construction. Mechanically we do, every mathematics student, they do very well, they write very good examples and very good exercises, but difficult to actually explain, and Professor explained very well. So I hand over the Professor to continue his session. Okay, thank you. Please, Professor.
Okay, before starting, please ask at least one question. Anyone?
Why supremum property is called completeness?
Completeness. What we proved? At least outline.
Why supremum property is called completeness?
That's it. The denseness, completeness, using completeness only we are able to prove that it is, as a metric space also it is complete. Completeness, without this LUB axiom, we cannot even define irrational. Yeah, see rational, up to rational, okay. So we can, some are axiomatic way, we can define either assuming natural number or even start with a field, then define a positive number. Positive mean which we are arbitrary non-empty field, plus and dot are there, it is a field. Then we define a set, a quality. Positive means it should behave, good student mean we have some idea, like that positive mean x positive, y positive mean x plus y positive. X not equal to 0 mean either x positive or x may be minus 2 type. X positive or minus x positive, but not both, like that we define. Then using that we prove even one is positive. One positive, then one positive using algebraic concept, then 1 plus 1 positive, xy positive means x equal to 1, y equal to 1, 1 plus 1 positive, that we call notation 2 like alphabets, then 2 plus 1 positive like that, positive integer, then rational we can define. Go for irrational all, we need the completeness, LUB axiom. Even that should be defined. One way of defining is R is complete. See, we can define, for example, this sequence. How you will, we are all familiar. 1 plus 1 by n whole power n. As a sequence, you call it xn or sn. What type? It's a rational sequence of rational number. Okay, n equal to 1, 1 plus 1 by 2, n equal to 1 plus 1 by 2 whole square and so on. It converges where? It converges to where?
Positive or negative?
Okay. Whether first is converges, why it converges? 1 plus 1 by n whole power n. This is even very basic level, BSc first year or second year when it is a, again you will use, it is a monotonically increasing sequence. If it is increasing means, when it converges, it has an upper bound. See, again this is very trivial. Increasing means what? Only just x1 less than or equal to x2 less than or equal to x3. Increasing. It has an upper bound means there exists some alpha, so all the xn less than or equal to alpha. As a set, like this is our set. This set has an upper bound. The monotonically increasing sequence, it has an upper bound means it converges, where it converges? To its least upper bound, supremum. There also, even to prove that it converges, you need LUB axiom, completeness. Then you get this, what we call it, what is this? It converges, it is a rational sequence, sequence of rational number. It converges to some real number. What do you call that real number? Familiar? Not familiar? This, for example, we know that this also. Okay, more general, right? E power x, that is 1 plus x squared by 2 factorial plus, we know this E 1 plus 1 plus 1 by 2 factorial like that. This converges to sequence of partial sum. This also, both the sequence will converge to that common element, we call it E. See, even that to get irrational number, completeness axiom we need. Okay, it is a simple exercise. Least upper bound, among the upper bound it is least. Suppose alpha is least upper bound of a set A. Take any epsilon, positive. What can you say about alpha minus epsilon? Already alpha is the least among the upper bound. From there we remove alpha minus epsilon or alpha minus 1 by n. That will not be an upper bound. That means there will exist some element xn greater than that element, then you, yeah.
That bounded set has supremum and infimum.
Yeah, we can. Bounded set will have supremum and, because it has a upper bound as well as lower bound.
There are so many supremum. No, supremum is only one.
Supremum only one.
But this supremum is necessary to lie in the set of matrices.
Supremum, what is open interval 0, 1? See, if we take the open interval 0, 1, this is our set A. What is an upper bound? 1 is an upper bound. Anything greater than 1 also? What is the least upper bound? 1. 1 is not in the?
Not necessary.
Not necessary. Yeah, upper bound.
It may or may not.
It may, that's it. Even the by definition itself, we say that upper bound need not be in that set. Okay, so it may be there. We don't say need not be mean. So like here itself, instead of open 0, now if we take closed, Now what is? Now it is there. In general, here it is. Some cases it may be there if you have a closed set. Okay. In fact, alpha equal to supremum or least upper bound of a set A means we can get a sequence xn in A such that xn using LEB, that alpha minus 1 by n, not an upper bound. Then using that we will get a sequence which converges to alpha. That's as Professor Murthy said, these are all simple exercise. Okay. Yeah, very good. Any other? Clear? Okay. Anything else? The main thing that should be proved.
I think, sir, one question. What I noticed is the students facing is because sometimes what happens, we have the inequality. Contraction, it is an inequality. And there is another technique also to show that the sequence is a Cauchy sequence. And even sometimes we do one thing is we are comparing the space, that the space is complete. Based on that completion we go for
correct.
So even for the Cauchiness also, for the inequality, in some cases what we do is we take the supremums in contractions.
Contraction, I mean what there will get is again that the 1 plus the geometric series.
So
geometric series will use.
Facing the problem why supremum should be taken. That is one issue. And another one is the facing is like we are using the mod of x minus y is less than something something. Okay. This is fine. The mod of x minus y is greater than or equal to this one. But mod of x minus y can be less than something.
Yeah, it can be less than something. It is less than also greater than also. We don't.
Yeah, but there they are having some difficulty.
No. Convergence mean only converges to a point x mean whatever may be the neighborhood. However, that's however also mean the radius or epsilon radius. Center at x, radius epsilon. That's an open interval x minus epsilon, x plus epsilon. Except finitely many, all are inside. Okay. So all are inside mean mod xn minus x less than epsilon. But some other, suppose all are 2, 2, 2. If the mod xn minus x come closer, suppose even the secant 1, 1 by 2, 1 by 3. Some cases, suppose our epsilon is 1 by 10. Modulus of 1 minus 1 by 3 may be greater than that, we don't bother. What we need is after some stage, except finitely many, all should be inside, in the neighborhood. It approaches, I am approaching to you. That means after some stage I am walking towards you, after some point of time all we come very closer. That's why we talk about neighborhood. Okay.
So they have some this type of problem, taking the infimum of the supremums.
Yeah, limit supremum, limit infimum, that is different.
And another is by taking the orbital point and starting with the orbital point and then the construction of the sequence.
That is different.
There are some ways are there. So these are some problems I found.
You have the
students are facing.
That's correct.
It means not only my students, actually the the young generation is facing the problem.
Okay.
So if it can be dealt, I think.
Anything else? No. You want any, like whatever Professor Murthy suggests, anything, if I know I will tell. You can ask. Any? Okay, now we are going to little advanced level. What is reflexive Banach space? And then Jones lemma, what is called compact, all of you know. Compact, in a metric space when you say a set is compact, using, there are different versions. What you are familiar? A subset of a metric space is compact if and only if every open cover. See, that's what it is. Some work can be done by a large group of people. Collection of open set covers the set A. But that is compact means that large collection we don't need. From there we can extract a finitely many member so that A will be A1 union A2 like that.
Sir, I think maybe you can try to explain this. In
R, and then the infinite dimension with the one example. So
Yeah.
get the
R, yeah, I will give you the example of, R is nothing but, when you say some subset of R is compact, it is closed and bounded. In fact, R, there are different versions, complete and totally bounded. Again, closed interval A comma B compact, you can use LEB axiom. Okay? You want that proof? Okay, not the explain the concept only.
Compact.
In R mean?
And then infinite dimension.
Yeah, compact in R mean it is just a closed and bounded set. See, I will give the idea. For here also we use the LEB axiom. See, A is a non-empty, closed and bounded. This I am writing for bounded subset of R. Then it is compact. Closed and bounded means what? It will have lower bound as well as upper bound. That's what we will have. There exists A comma B belongs to R, A less than B, so that A is a subset of closed interval A comma B. In fact, what is enough to prove? Closed interval A comma B is compact. Then closed subset of a compact space is compact. See, then what we will do here, at least I will give the outline. What is script A is a collection of open set in R, such that I am not writing collection of open sets, such that A is a subset of, it is a cover mean I used a different notation. Here we have fixed the set as A, or we will call it the closed interval A comma B. So that closed interval A comma B is subset of, now forget about this, we want to prove that this set is compact. I can use some other notation also, just I use A. A belongs to script A means what? A is a open set. We can assume they are all non-empty set. Empty set is there, remove also no problem now. Still it will cover. That means what? A will be, small a will be belongs to one of the member. A, small a will belongs to some capital A, where A belongs for some A in script A. What is script A? A is an open set. Small a belongs to that open set means it is an interior point. Interior point you know, no? What is interior point? There will exist a neighborhood. Here an open set in R itself we can take. We can find a open set. This is completely contained in sorry, this type of right. A minus epsilon, A plus epsilon. A is an interior point means it is inside, properly inside. That means not only just it is a point, some neighborhood of that point should be in the set A, interior point. That means up to where we have covered. Now A, this set is a subset of A. A, or we can call it A1 for some A1 belongs to some set A1. That means from A to here we have covered. Okay, or if you want even you can call it A plus epsilon by 2. So that closed interval. A2, where A is up to here we have covered. Okay, this is contained in A, this. Again, this A plus epsilon by 2 you take, again that is will be in closed AB. That means A plus epsilon by 2 also will some other A2. I mean it may be same. It will be one of the open set.
So this is the finite collections of open set?
No, script A is a collection of open set. It is a cover for closed interval A comma B, open cover. Script A already it is finite mean, where is the question of finding a finite subcollection? Already it is a compact, only 4 or 5, only 5 of them is attending. It is, I mean, if the collection is very large, still we can get finitely many member. Here finitely mean doesn't mean that very small or anything. Finite mean finite, it may be 1 million or some finite A1, A2, AN for some AN. So that closed A comma B is subset of that. So, yeah. Yeah. Every open cover of the set A has a finite subcover. Finite subcover means there exists a natural number n and that many A1, A2, AN belongs to script A, such that whichever we are calling compact, that set is a subset of A1 union A2 union AN. Correct?
That becomes finite.
That should be finite. Yeah. That then only we call it compact. See, that's it here. Already we have covered up to epsilon by up to here. Again epsilon by 2 is an open set. Then right side will cover. Like that A plus some n epsilon for large n will be greater than B. N is finite. That means essentially it is totally bounded. Closed interval is complete and totally bounded. It is compact. Or even you can use LUB axiom. To prove closed interval A comma B, if you see topology by Mungers or any book, most of the book, they will prove using LUB axiom. Even interval is connected, use LUB axiom. Interval is closed interval is compact, closed and bounded, LUB axiom. So you cannot avoid LUB axiom in real analysis. Okay, clear? Yeah, any other thing you want? No. Yeah. Okay, so topology you are all familiar, no? Oh, already.
So if you have any one more question, then you can ask, then we will finish for today. And then
okay, then tomorrow we will introduce what is Jones lemma and reflexive, then we will do related fixed point theorem. Because Jones lemma, how many of you have never heard? Oh, not heard. See, Jones lemma is simple. How many? Is a university, maths department, only final year MSc student. You get gold medal, no? University is having?
Yes, yes.
First MSc maths 1, will assume that only 1 gold medal. Physics 1 gold medal. Chemistry 1 gold. Each department will have 1 gold medal. We'll ask X is set of all students, only final year students. Then we'll define xy belongs to capital X, X is less than or equal to Y mean, we conduct a test, marks obtained by the student, first student is marked as X. X is less than or equal to Y mean, we call it that student A is less than or equal to other student. Then this is called a partially ordered set. Partial order mean reflexive, what else? Transitive, what is anti-symmetry? We are against symmetry. Symmetry should not happen except the trivial case. Meaning is symmetry, suppose for some xy in our so-called partial order set, x less than or equal to y. Symmetry means y less than or equal to x. But symmetry, we are against symmetry. That means what? Pardon? Equal, y. Because if x less than or equal to y, x not equal to y means symmetry happens. We are against symmetry. Y, that but reflexive is there. X less than or equal to, that's not against symmetry. We have a non-empty partial order set. Chain means any two elements are related. One on the top we can arrange. X less than or equal to y or y less than or equal to chain. Every chain has an upper bound. Then it has a maximal element. The topper in mass may be 90 marks. Topper in chemistry they are very liberal, maybe 99. But they are not related. Each topper is So that's what mass will arrange only one topper like that. Here one topper, physics, like that. Here one element here and another element not related. Neither x related to y nor y related to x. But this is a chain, mean here in a chain mean if xy belongs chain mean it is a set. Either x less than or equal to y or y less than or equal to x. Then we have a partially ordered set. Next what you have to check? Every chain, another name is totally ordered set. Meaning is A is a non-empty set. If we take xy belongs to A, either x less than or equal to y or y less than or equal to x. Then such a set we call it chain. Then it has an upper bound. Upper bound same way. X less than or equal to x naught for all x in A mean that x naught upper bound. If so, it has at least, it has a maximal element. What is maximal element mean? He is topper already. Suppose mathematics x naught is topper mean x naught cannot be less than or equal to some other y. X naught less than or equal to y mean that is possible only y equal to x naught. Okay, this you revise and come. Also in functional analysis that is called a canonical embedding. That map is on to mean reflexive. Closed bounded convex set or a unit ball in a nonlinear space need not be compact. As professor he says that, for example, you refer this. En we know that 0 0 1. This is a sequence in where? Infinite dimensional given. Which infinite dimensional you like? Okay, you tell. One infinite dimensional space containing. Okay, L2 we'll see tomorrow. Suppose these are L2 mean square summable. Each element is finite, convergence, x equal to xn. Then here they are all in L2. This is closed and bounded set. Compact in metric space mean every sequence will have a subsequence which converges to an element in that. Suppose this is an element in the unit ball. Okay. So what will happen? Distance between En and Em? N not equal to M mean? See, N here, suppose Em 0 0 0 0 0 1 like that. Then distance between summation 1 summation mod xn minus 1 1 another one will come. So root 2 or whatever, it cannot be less than, it will not be even a Cauchy sequence. In fact, what is interesting is using Banach theorem. If the unit ball set of all x either norm x less than or equal to 1, if that set is compact, the vector space is finite dimensional. If that way will, that's it. This is infinite dimensional mean unit ball can never become compact. What is our interest is compact with respect to some topology. That topology is called topology which make the smallest topology which make every f belongs to the dual space continuous. That we will discuss tomorrow. Then will, that is called weakly compact with respect to some, not the topology induced by the norm, topology, the weak topology. Norm will have topology induced by the norm is called strong topology. Weak topology, there the unit ball is compact will become, the canonical embedding is onto. That we will discuss tomorrow. They want to stop. Okay, thank you.
Okay, so thank you very much for I think we must suggest you, because for the tomorrow lecture, maybe you should try to go to the some of non-linear space. Get some time here. Try to learn non-linear space and also some kind of electric space. What do you mean by compact? What is LP kind of thing? Maybe also CAD space of all conditional functions.
If you have to go through and please come with doubt. If you have doubt, you are welcome, we will discuss, then we will proceed to proper fixed point theory, little advanced.
Okay, tomorrow scheduling will be done, everything.